All right, it is 8 o'clock. I see people still trickling in here. Tom, did you want to say a few words?
Yeah, let me get started. Good morning, good afternoon, good evening. I've noticed people from various different time zones. Thank you again for joining us for IPPW 2021 Session 2. That's going to be on Mars exploration. I am Sam Detta, one of the POC chairs, Program Organizing Chairs, and I wanted to, again, go over the rules. Once again, if you're not a speaker today, please don't unmute and speak. If you have any questions, put them in the chat window, and the session chairs, the moderators are all looking at the chat window, and we'll make sure that your questions get asked to the speaker or asked to the general audience when the time comes. The session is getting recorded, and the recording of the session, as well as all the posters and presentations that are being shown today, will be on the IPPW archive side within a week. So just check back on the main IPPW website, click on the archive, and check back in a week, and you will see all the presentations, all the posters, all the videos, both from the posters and the session. And with that, I'm going to just hand it over to Gregory Villar, who's going to start the session.
All right, good morning, good afternoon, and good evening, everyone. I just want to start off by saying I'm very excited to be here, and I miss everyone so much. And just to make sure I have everyone's attention, why don't we all do some sort of reaction? On the bottom of your screen, there's a little smiley face with a plus sign. Feel free to throw out a reaction so I know you're listening and happy to see me too. All right, thanks. I just wanted to let everyone know, I think my first IPPW was in 2014 in Pasadena. And, you know, for all the students out there and the new members, I hope you stick with us, because I remember the moment I stepped into the conference, it just felt like a family, right? And I think that was one of the best parts of IPPW. And since then, there has been a lot of amazing memories that I personally generated, both professionally and in friendships. And some of the cool things that we have in this conference is, I remember kind of the year that Schiaparelli happened, and when we had them give talk at IPPW, there are a lot of us who kind of talked to the Schiaparelli team and kind of helped brainstorm what happened. And that was a really cool thing to see kind of on the sides happening as well. And, you know, even in our events after IPPW, like at nighttime when we were hanging out at, you know, certain venues or just talking to each other in drinks, I remember there was a time at the hotel lobby where a lot of us were playing drinking games, but people like Dave Way and Ian Clark were just kind of on their little note tag talking about kind of parachute equations and stuff like that. So it's really such a great community, and I'm excited that I've been part of this community for about 8 years or so. So I really hope you guys all stay tuned after the session. You know, everyone knows that this year has been a big year for Mars. We've had a lot of great missions there, and we've jam-packed a good agenda today. An hour of that would be dedicated to the Mars 2020 mission. And as Sam mentioned, you know, we'll have the materials posted here, and you know, I hope you guys enjoy kind of the whole set of slides that we have today. So if we can quickly go to the schedule, and we can walk everyone through that. Let's see. All right. So thank you, Tim. All right. So today, I just did a welcome here, and up next we'll have Lori Glaze. Thank you, our keynote speaker. Then after Lori, we will have a series of invited 2020 talks. So we'll hear about from the 2020 team, generally how it went for EDL. Spoiler alert, it worked. And then we'll do a quick break, and when we come back from the break, we'll have a poster Q&A for some of the posters we have for our session. And then we have 2 more invited talks. So we have Sanjay from ESA that will talk about the future of Mars exploration for ESA. And then we have Zach Putnam talking about revolutionizing the access to the Mars surface. And then after that, we will go into our oral presentations. Today we have 6 on the schedule. And the goal is to be done before noon Pacific, where we'll, soon before that, we'll do our closing remarks. And a quick reminder to all of the presenters, we'll keep on to this, but the allocated time is 10 minutes, so I hope you all practice your presentations. And we've allocated an extra 2 minutes for questions. This is true for everyone except, I believe, Lori. So please stick to time, and you know, at some point, if we think we have access to your slides, and if we think you're going to overrun, we'll just kind of give you a little notice, or Maybe if we're really, really cranky, we'll just mute you. Okay, so I think with that, we are ready to go. And I'm going to hand it over to Michelle to introduce our keynote speaker.
Thanks, Gregory. I want to thank Gregory and Oscar Kratikin for being the session co-chairs for this Mars exploration session. It's been a pleasure to work with them, as usual, on organizing the session. So thanks, Gregory, for kicking us off. So yes, we have today we are honored and privileged to have as our keynote speaker for this session, Dr. Lori Glaze. Dr. Glaze is the Director of Planetary Science Division of NASA's Science Mission Directorate. Planetary science is focused on spaceflight missions and scientific research that addresses fundamental questions of solar system formation and evolution, including understanding planetary environments that can or could have in the past support life. So Lori's division is the one that we in the International Planetary Probe community work with most within NASA's Science Mission Directorate. Prior to headquarters, Dr. Glaze served as the Chief of Planetary Geology, Geophysics, and Geochemistry Laboratory at the Goddard Space Flight Center in Greenbelt, Maryland, and as the Deputy Director of Goddard's Solar System Exploration Division. Her research interests include physical processes in terrestrial and planetary volcanology, atmospheric transport and diffusion processes, and geologic mass movements. Her work focused on data analysis and theoretical modeling of surface processes on all of the terrestrial solar system bodies, particularly the Earth, Venus, Mars, the Moon, and Io. Dr. Glaze was a member of the Inner Planets panel during the 2013 Planetary Science Decadal Survey and had a role on the executive committee of NASA's Venus Exploration Analysis Group, or VEXAG, for several years, serving as the group's chair from 2013 to 2017. Dr. Glaze was a member of the Planetary Science Subcommittee from 2011 to 2013 as well. She has been involved in many NASA-sponsored Venus mission concept formulation studies, including as a team member of the Venus Flagship Science and Technology Definition Team and as science champion for the Venus Mobile Explorer in 2010, and co-science champion for the Venus Intrepid Tessera lander in 2010. Until her move to headquarters, she was also the principal investigator of the Deep Atmosphere Investigation of Noble Gases, Chemistry, and Imaging, or Da Vinci mission concept, which you'll notice the name Da Vinci Plus was recently selected as a discovery mission by NASA. So we're so excited for Lori and for that team. Dr. Glaze was born in Texas. She graduated from the University of Texas, Arlington with a BA and MS in physics. She received a PhD in environmental science from Lancaster University in the United Kingdom. She has also previously worked at the Jet Propulsion Laboratory and at Proximy Research as Vice President and Senior Research Scientist. Dr. Glaze has been a good friend and strong supporter and attendee of the International Planetary Probe community. So please give her a warm virtual welcome and enjoy her presentation. We'll have time for Q&A at the end of her talk, so please put any questions into the chat. So Lori, take it away.
Thank you so much for that wonderful introduction, Michelle. That was great. I could not be happier to be here at the IPPW. I loved, Gregory mentioned when his first IPPW was, mine was in 2010 in Barcelona. And as you can tell from Michelle's introduction, I've had a long-standing interest in missions that involve atmospheric entry. Many of the mission studies that I did for Venus were very focused on trying to get to the surface of Venus or to study the atmosphere of Venus. So a long interest in planetary probes, atmospheric entry, and so this community is very important to me as a scientist, but now as the director for NASA's Planetary Science Division, I fully recognize the importance of this community to many of the destinations that are critical to planetary science and our future. I also really miss that this meeting isn't in person. I'm really looking forward to future in-person IPPW meetings. I know this is a great community, and I love interacting with all of the folks. But I'm really excited to talk to you here today about Mars exploration. In particular, as was noted, it's been an incredible year for Mars exploration, including the U.S., UAE, and China all launching spacecraft that are now successfully beginning their science missions at Mars and doing great work at Mars. So it's really a great opportunity to talk about Mars exploration. And I'm going to give some of my perspectives from the NASA point of view. So if we can go to the next slide, please. Just a quick snapshot. This is our overall planetary science portfolio. I always like to start with this because it is an incredible time for planetary science across the entire solar system. Our NASA portfolio now includes 39 missions in that portfolio, either in development or in operations. Some of those missions led by NASA, some where we have NASA contributions on missions led by all of our international partners, but a really fantastic portfolio doing amazing science across the solar system. Today I'm going to focus, of course, on Mars primarily, although I will give you a few highlights of some other things going on in the solar system that might be of interest to this community. But at Mars, our Mars portfolio, you can see in that little inset box is almost a third of our missions are really focused on Mars exploration, which is really an amazing statement about just how important Mars is to helping us understand planetary science in general. So a fantastic destination and lots of great science going on there. So if I can go on to the next slide, please. This, I'm sure many of you have seen this over and over and over again. I don't get tired of watching it. The first time we were ever able to really watch the entire entry and descent of a mission on any other planet, but on Mars particularly impressive. You saw the parachute deployment there. Now you can see the system looking at the surface and trying to find a safe place to land, locking in on that using the terrain relative navigation technology, and then once that location is identified, descending straight down into that location and eventually beginning to lower down on the tethers from the sky crane and safely touch down on the surface of Mars with the Perseverance rover. An incredible accomplishment by the entire Mars 2020 team. I know you're going to hear a lot more about that entry and descent later on and all of the capabilities that made that possible. But what an amazing moment that was when we got to all hear those magic words, touchdown confirmed. So just an incredible moment on February 18th. If we can go on to the next slide, please. I love to show this slide as well. A wonderful image showing a Jezero crater on Mars, and to the left of the image, you can see the river delta, which is our ultimate destination, or one of the ultimate destinations that we hope to explore with the Perseverance rover. That river delta is so important because it tells us just visually from orbit and using remote sensing observations that water once flowing water once came into the Jezero crater and flowed into a standing body of water where those sediments were deposited. And this occurred about 3.5 billion years ago. And we believe that if the conditions were supportive of life starting to take hold on Mars, which is about the same time they started to take hold on Earth, similar conditions existed on Mars, it's possible that those remnants of that early life would be preserved in that river delta that you can see to the left. So really exciting target for us. What you can see here, of course, is the the rover itself coming down on the parachute as captured by the Mars Reconnaissance Orbiter, which is just a beautiful, beautiful sight to see. We can go on to the next slide, please. I'll just give a few words about why this mission is so important to science from so many different perspectives. I mentioned that we picked an amazing landing site in Jezero Crater that is particularly intriguing because of that ancient river delta that could potentially preserve these biosignatures, the complex molecules and these potential markers of early microbial life that could be preserved in that river delta. But in addition to that, there are other really important geologic features within that crater that can help us not only understand that potential for life, but understand the environment that was present on Mars at that time. Rocks that can help us, if we understand the geology, better constrain just how old that crater is, how old the deposits are, and again, what that environment was like when that river delta was in place. So very, very important geology goals of this mission to understand the location where we've landed. And then that astrobiology goal, which is really understanding the habitability of Jezero Crater and, again, looking for those potential signs of early life that may have been preserved. And then the most important part of this mission, we're going to do a lot of great remote sensing science while we're on the surface with the incredible payload that we have. But one of the most important things we're going to do is actually core into the soils and the rock in Jezero Crater in multiple different locations and collect some of that rock to be eventually brought back to Earth. This is incredibly important to answer some of the questions we want to answer. It's going to require much larger laboratories and instruments and personnel around the globe to answer those questions. And by bringing those samples back, we can take advantage of that full breadth of instrumentation, the full expertise of our international science community, and also preserve some of those samples for the future to use instruments that haven't been invented yet and answer questions we don't even know how to ask yet. So it's incredibly important to collect those samples with perseverance, and I'll talk a little bit more about how we'll get them back in just a moment. In addition to those major science goals and objectives of the Mars 2020 mission and for Perseverance, we're also doing a lot of things to help us prepare for future human exploration. This has become even stronger goal as we are now returning to the moon with humans and thinking about eventually landing humans on Mars. And so we want to make sure that we're preparing and are as best prepared as we possibly can for that human exploration that's coming. Next slide, please. So this again is just showing where we've landed. You can see the landing spot identified in that top left image, showing some of the geologic units that are present. Thank you for the cursor showing that. Thank you. You can see our landing spot. You can also see down below, I believe that this is as of June 29th, so a week ago or so, you can see the path that Perseverance has taken so far, and you can see where she's currently located down there where the little blue marker is with the rover. There's also a little marker for the helicopter showing where the helicopter is as well, kind of keeping pace. But the main thing I wanted to show on this slide, just to, I'm sure you'll hear a lot more about this as well, but the hazard map that's shown on the top right, I love this image that shows the places that were safe for Perseverance to land in blue and those that were hazardous or that we needed to avoid in red, and just recognizing how challenging it is to land in Jezero Crater, and that prior to Mars 2020, we would not have been able to select Jezero as a landing site, but because of the incredible technology and advancements of this team to develop the terrain relative navigation capabilities allowed us to pick Jezero with its exciting science and actually safely navigate to a safe landing spot that you can see carefully nested between all of the red in a little blue spot. And I'm sure you'll hear a lot more about that in a little bit this morning. Going on to the next slide, please. I already mentioned we've got an amazing science payload on this mission, including incredible science instruments that are going to be able to see beneath the surface with ground-penetrating radar, being able to, of course, image everything that we see in our surroundings. I'm sure you've seen thousands of images already coming back by Perseverance. But also be able to, in particular, look for those rocks and samples that might be of most interest for us to bring back. So we have instruments on board with Pixel and Sherlock that are, and SuperCam, that are specifically focused on trying to understand the chemical composition of the rocks and help us identify those rocks that we'd like to bring back to Earth eventually. We also, of course, carry the META package, which is giving us great information about the weather on the surface of Mars, again, helping us prepare for human exploration, and MOXIE, which is an experiment to convert the carbon dioxide atmosphere of Mars into breathable oxygen. And I know they've already conducted a handful of experiments, I'm not sure how many at this point, but several, where they've successfully converted the carbon dioxide into very pure oxygen at a rate that's about, the rate of conversion is about equivalent to a medium-sized tree on Earth. So that's a great accomplishment, again, in preparation for human exploration, where we'll need to take advantage of those resources that can be found in situ on Mars to either provide breathable oxygen for our human explorers or potentially for fuel to get back off of the surface of Mars. You can see in the inset box over to the right several of the technologies that were demonstrated on Mars with Mars 2020. It's incredibly important with each of these missions that we push the boundaries and demonstrate the capabilities that we need for the future. And I know you're going to hear a lot more about these in a bit, but these were all very successfully demonstrated with the Mars 2020 entry and descent. The Medley 2, which was the instrumentation of the heat shield as it came in, allows us to gather detailed information that will help us build more efficient heat shields in the future. The terrain relative navigation I already spoke to, that allowed us to really refine our entry and to safely land in an area that is actually has quite a few hazards, but able to successfully do that. And then the third technology demonstration is actually the Mars helicopter, which demonstrated for the first time ever powered and controlled flight on another planet or another body other than Earth. An incredible achievement. Successfully has already completed its 5 technology demonstration flights and has now shifted over into an operational demonstration phase, which is trying to demonstrate just how such an asset like an aerial platform could be used to augment and enhance the science return from a primary payload such as a rover or a human exploration sortie. So the helicopter is doing amazing things. They just completed their 9th flight on July 5th, traversing, I believe, over 600 meters over undulating terrain, which was a challenge for that technology, but doing a great job in providing amazing data back, not just to us as fans of the helicopter, but amazing data back to the science team that they can use in their planning for the Perseverance science. So go on to the next slide, please. So talking about the helicopter, these are just some of my favorite views of the helicopter. On the top left, you can see one of the helicopter flights where it took off, ascended to about 10 meters, and then you're going to see it fly off to the right and go out of the scene. And then in a few moments later, it will return back into the field of view. And then on the top right, you can actually see some of the imaging taken by the helicopter looking down. You can see its shadow on the surface. Just amazing how well its navigational cameras have worked as well, and its navigational software able to control its flight and actually now search out its own landing sites, doing a great job. Next slide, please. So as I said, one of the most important things that Mars 2020 is going to do is going to do a lot of amazing science on the surface of Mars, regardless with its remote sensing instruments, but it does have a goal of collecting some samples that we'd like to bring back to Earth. And so Mars 2020 is, in fact, the first leg in Mars sample return. And so you can see on the left that first gray bar, that is Mars 2020 with its successful launch and landing on the surface. We've successfully begun that sample return campaign, and we're now partnering with the European Space Agency to develop the next set of missions that will bring those precious samples back to Earth. One of those missions will be the Earth Return Orbiter that's led by the European Space Agency, and that launch will send an orbiter that will go into Mars orbit, act as a relay during the entry, descent, and landing of the Sample Retrieval Lander, which is led by NASA. And you can see that Sample Retrieval Lander lands on Mars carrying a sample fetch rover that is capable of going out and collecting those samples and bringing them back to the lander if Mars 2020 is still healthy, if Perseverance is still healthy. We also have the capability for the Perseverance rover to bring samples back to the lander. And then once we've loaded up the sample return capsule, the orbiting sample container, those will then be launched from the surface of Mars with the Mars Ascent Vehicle. That orbiting sample is then captured by the Earth Return Orbiter and returned back to Earth. And so with this mission, you can see three great opportunities for entry, descent, and landing. The first one already completed on Mars. We'll have a second to deliver that sample retrieval lander, and then a third entry back on Earth to bring the samples back here. So I know a mission, a set of missions that will be very much of interest to this science community. Going on to the next slide, please. So just thinking a little more broadly about Mars exploration, in addition to Perseverance and all of the other missions we currently have on Mars and our plans for Mars sample return, we're also collaborating closely with the Japanese Space Agency on the Mars Moons Explorer mission. This is another sample return mission where NASA will be providing an instrument, MEGANE, which is a gamma ray and neutron spectrometer that will be looking at the surfaces of Phobos and Deimos to help characterize their chemical composition, their elemental composition of those two moons. And then ultimately the JAXA spacecraft will land on the surface of Phobos and collect samples. And NASA's providing one of those sampling systems, JAXA's providing the other. We hope to collect samples of Phobos and again bring those samples back to Earth with an atmospheric entry back on Earth. I believe it's in 2029. The mission actually is to launch in 2024. Get those samples back at the end of the decade. Those samples would do their reentry into Australia, just as some of the other JAXA missions, Hayabusa 1 and Hayabusa 2, have done. So another great opportunity for entry, descent, and landing, and another great opportunity for us to get more samples back to Earth to study. Next slide, please. And I know that this is a Mars exploration session, but I'm going to take advantage of my opportunity to speak about some of the other exciting planetary missions that are ongoing that also are relevant to the planetary probe community and particularly the entry, descent, and landing community. OSIRIS-REx is our mission to explore the asteroid Bennu. OSIRIS-REx successfully, last October, collected a sample on the surface of Bennu, and yet again, another example of where we really want to bring those samples back to Earth here so that we can study them in our laboratories. Asteroids such as Bennu are remnants of the early building blocks of our solar system. As the solar system started to form, materials started to stick together and start to form some of these asteroids. Some of those asteroids continued to collide and build into protoplanets and eventually into the planets that we have today. And so these asteroids like Bennu are kind of the leftover pieces that are still present, orbiting around the sun out in the solar system. So being able to collect samples of these asteroids gives us a lot of insight into exactly what the early solar system was made of and how things like organic molecules and water would have been delivered to Earth and delivered to other bodies in the solar system. Those important building blocks for the life as we know it on Earth today, delivered by asteroids like Bennu. So by studying Bennu, which we've mapped out very detailed with remote sensing observations and now collected a sample, we collected that sample back in October. We collected so much sample that we were afraid we were losing some. You can see in the top right the sampling head. After the sampling event, actually particles escaping from that sample head. And so we very quickly tucked it away into the atmospheric entry capsule, as you can see it getting tucked away there. And then on May 10th, the OSIRIS-REx spacecraft began its journey back to Earth and will arrive back on Earth in September 2023. Where that atmospheric entry capsule that you see there will enter into Earth's atmosphere and land in the Utah desert in September of 2023. Next slide, please. I did want to mention that the sister mission to OSIRIS-REx is the JAXA-led Hayabusa 2 mission. Hayabusa 2 also is visiting an asteroid Ryugu. And JAXA successfully returned their sample of Ryugu back in December. And I wanted to mention that may be of interest to this community, that NASA supported that atmospheric reentry with our scientifically calibrated in-flight imagery team, the SciFly team. We supported this reentry with 2 Gulfstream 3 aircraft. This was an effort that required collaboration and partnership between NASA, JAXA, and the Australian Space Agency. As I said, the entry location was in Woomera, Australia. And I just wanted to point out that all of this was done during really the peak, one of the peaks of the pandemic in early December. The team was required to quarantine, very strict quarantine for multiple weeks in order to support this campaign, but we were able to get the aircraft over there, our full team, and to collect an incredible complement of observations from those 2 spacecraft across a broad spectral range from UV visible all the way out to the shortwave infrared. And you can see on the bottom right some of the data that were collected. We're in the process now doing our post-processing, but we were able to, I think, implement a new approach here, which is being able to do the flow field property binning, relating the measurements to the surface radiative heating, give us more information, and all of this will help directly inform how we develop our margins for future atmospheric entry vehicles. So really important observations there in support of our entry systems modeling work. Next slide, please. Also wanted to mention that the Dragonfly mission is now in its phase B. This is a mission funded through our New Frontiers line. And Dragonfly is a mission to explore Titan, an incredible mission that is now scheduled to launch in 2027 and deliver an octocopter, a multi-rotor landing system. And you'll see here in just a moment in this animation, as the entry shield opens, the helicopter coming out of the entry system and actually flying to the surface, as opposed to something similar to what we're used to seeing on Mars. You'll also notice in the top left corner of the animation that the time frame for a Titan entry is significantly longer than the 7 minutes of terror that we have on Mars. We're talking about an hour and a half or more to get to the surface. The atmosphere of Titan is very dense, and so it's cold, but very dense and much lower gravity than Earth. So we expect this to be a really interesting mission. It's going to, once it touches down, it has the ability to fly to more than 24 landing sites on the surface of Titan and traversing over 100 miles to explore a really broad, diverse set of geologic settings on the surface of Titan. Really exciting mission. Next, please. And then finally, I do have to mention Da Vinci. Michelle mentioned it at the top that in a former life of mine, before I went to NASA headquarters, I had a lot of involvement with this mission. When I went to headquarters, I had to step aside, and Jim Garvin is an incredible principal investigator leading this mission, doing a great job. And I couldn't be happier for them that they've been selected to go forward in the Discovery program. Again, another opportunity for atmospheric entry on Venus with a probe that will in a lot of ways mimic the entry of Pioneer Venus probe, the Pioneer Venus Large Probe, and collect atmospheric samples and measurements, doing in situ observations, in situ measurements, all the way down through the atmosphere, helping to characterize the environments, the evolution of the habitability on Venus over time, help us to better understand the history of water on Venus, and then using the full suite of observations to help us better interpret what the Venus-like exoplanets might look like and how we might identify those at multiple stages in their evolution based on what we learn from Da Vinci. So another exciting mission there. And I believe with that, I'm going to stop and take some questions if there are any. And I'll apologize for deviating a little from Mars exploration, but I just couldn't miss the opportunity to talk about the other cool stuff.
Thank you, Lori. That was awesome. It was really good to see all the exciting entry, descent, and landing opportunities we have throughout the solar system. We're very busy as a community right now, and that's awesome. So I haven't seen any questions for Lori in the chat, so I will go ahead and ask one. I know a couple years ago you had a small satellite, excuse me, of course my lawn guy is right here at this moment. Let me mute for a second.
The joys of living in virtual world, I know.
That's right. A couple years ago, you had a small sat opportunity for solar system exploration types of proposals. How do you see the small satellites playing in the solar system exploration of the future? And do you see them potentially evolving from, just interplanetary or orbital like Marco into the entry, descent, and landing world?
It's a great question, and I love that line of competed missions, the Simplex line. It's been challenging to offer another call. Our first 3 missions that were selected from Simplex are all doing very well. We've got Lunar Trailblazer and Escapade. Lunar Trailblazer, of course, going to the moon, doing remote sensing observations. Escapade being funded by the Heliophysics Division to go look at the atmosphere of Mars. And then the Janus mission, which is 2 spacecraft to explore 2 binary asteroid systems. And so those are doing very well, and I really would like to get another call out at some point. As soon as we have a good budget line that will allow us to do that, we will. But looking forward, I'm really hopeful that the decadal survey will provide us with some guidance. Our decadal survey is expected out next spring. Some guidance of how to balance our portfolio between the Simplex and Discovery and New Frontiers lines to allow us more opportunities with Simplex. And I very much do see opportunities in the future for much more complex missions that take advantage of those small platforms, particularly, as you say, missions that could do entry, descent, and landing, or carry something that does entry, descent, and landing, or even something, like a Marco, where you have missions that are perhaps more complex, going to the surface or into an atmosphere with a small sat that's doing the communications component. So I really do think there is a lot of trade space there and a lot of opportunity. There are some challenges in trying to do those now, but I know we're working on a lot of the technologies that are required. Propulsion is one of the key areas to be able to have adequate propulsion capabilities to go into orbit or to carry some of these larger payloads is going to be a challenge, but I think we'll get there.
Okay, thanks, Lori. If anybody can do it, I know our community can figure out how to make that achievable. I do have a question from Andrew Johnson. Any plans for a follow-on to Ingenuity?
That's a great question. And as of right now, we don't have any specific plans, but I think what we've shown with Ingenuity is the incredible, not just the ability to operate on Mars, but we're really showing now with the operational demonstration that there is a lot of benefit to this type of a platform, not just on Mars, but other places as well. So I think we've got a variety of competed opportunities, and it'll be great to see what comes in through those competed proposals. I think there's a lot of good, hopefully, good ideas out there to take advantage of that technology now that it's been demonstrated.
Yeah, absolutely. They've blazed the trail.
Yeah.
I have one from Ken Hibbard. Could Lori comment on future international collaboration on EDL missions, but also technology and capability advancement beyond what is already planned for MSR?
It's a good question. So right now, beyond MSR and MMX, which are the specific missions that we're partnering with other international agencies that have EDL components. We don't have anything specifically in the pipeline, but there are, of course, a lot of good opportunities out there, and this is another chance I can plug the decadal survey. May also come up with some good opportunities or priorities. I know that there are a variety of concepts out there that are being considered by the decadal survey that have very important entry, descent, and landing components. One being an Ice Giants mission that might carry a probe or potentially a lander for Triton. Other concepts, of course, are a Europa lander. So there are a variety of, I think, opportunities there that we may see that could unfold in the future, but we really need to see what some of those priorities are from the decadal survey. So I don't have anything specific that's already on the radar, but I think there's a lot of great opportunities out there and good opportunities to partner with other international agencies. As far as the technology and capability advancement, we're always looking to enhance and improve, particularly the entry system technologies. You've seen the advancement with the 2020 landing in the TRM, but we're going to need even more, pinpoint landing capabilities if we're going to eventually land humans on Mars. I believe, even with Mars sample return, we may have some need for more pinpoint landing if we want to try and land near, for example, where Perseverance is, so that we can take advantage of a delivery of some samples there. And then also, the continued refinement of our ability to model the thermal protection systems that are required, so that we can hopefully minimize our conservatism to allow us to carry more payload with us when we are entering the various environments. So we are investing in all of those things right now, by the way, already.
Yep, thank you, Lori. And we have some really good partnerships with different international organizations on those modeling efforts and testing efforts, as well as instrumentation. So, yeah, it's great to see. We have one more question, but I think we're going to move on and transition to our Mars 2020 talk. So, Lori, if you do have the opportunity and could respond to that question in the chat, that would be great. But I want to thank Lori again for her time and just a fantastic presentation as usual. And we look forward to seeing you next year in Monterey. And thank you again for all your support of this community.
Thank you. And I will answer in the chat. Thank you.
Thank you.
Great to see everybody.
You too. Okay, Gregory, back over to you.
All right. Thank you again, Michelle and Lori. and we are now approaching the Mars 2020 section of our session. And, I'm very lucky to have been working on Mars 2020 for the past 8 years or so. I think I started in 2013 when Al gave me a call and said, hey, do you want to come work on our team? And without hesitation, I said yes. So we have a great line of speakers here. And, in addition to seeing kind of 2020 develop from like the ground up, I think one of my most favorite experiences was working with all the people, including the folks you'll hear about today. And so first up, we have Al Chen. Al Chen was the entry, descent, and landing phase lead for the Mars 2020 mission. Prior to that, he was the flight dynamics and operations lead for the Mars Science Laboratory EDL team, culminating in the successful landing of the Curiosity rover in 2012. Though he is perhaps best known as the narrator of the briefly popular free Xbox Connect game, Mars Rover Landing. Go get that now if you have not. Al is a principal engineer in the Entry, Descent, and Landing Systems and Advanced Technologies group at JPL. He holds a bachelor's and master's degree in aeronautics and astronautics from MIT and an MBA from the University of California, Los Angeles. For that, I'm going to pass it along to Al Chen.
Thanks, Gregory. I guess I'd say thanks for having me back here. It's a pleasure to be back at IPPW, even if only from a spare bedroom. Lori did a great job giving a great overview of Mars 2020 in her talk. So all I have to do is give a quick overview of the EDL system and then get out of the way so that Andrew, Todd, Paul, and Ian can dive into the fun details a bit. So I'll try to save them most of the time if we can. So let's jump ahead to the next slide. So just as a reminder of what we were up against on Mars 2020, we started with an EDL system that landed Curiosity and a goal to try to stay as close as possible to that heritage. But that also meant dealing with things that didn't go quite right and risks that we learned about along the way. And as the mission itself matured, the rover got bigger. Perseverance ended up being about 130 kilos or so, 14% heavier than Curiosity. So we had to deal with that. And of course, as Lori talked about too, we started to want to go to much more dangerous sites to do the science mission that we're trying to do. So that necessitated some new capabilities like range trigger and TRN that we'll talk a little bit about. And we had to include those without breaking the heritage from Curiosity. And of course, over the last year, as the rest of us had to deal with as well, we had to make that final push to launch pad and of course, launch, operate, and land Perseverance all during this pandemic. So that was an additional challenge we didn't see coming. If you go to the next slide, something that IPPW fans that come regularly have seen a lot of, but just as a reminder, the things that we tried to do to reduce risk from MSL, things that we did to try to increase the robustness of our system. First, of course, was fixing an error that we had on MSL, which is that we touched down at a different velocity than we had intended, a little slower than we had intended, due to local gravity being a little different than we had expected. And in response to that, we developed high-fidelity terrain models to kind of combat that. And that worked out pretty well for us, as I'm sure Paul will talk about a little bit later on. The second thing we looked at was parachute-induced, the parachute deployment-induced navigation error. This is kind of from the deployment of that parachute ringing our system, really ringing those panels that the inertial measurement units were on, and causing a little bit of concern about navigational errors. So we took some steps there in terms of softening the blow a little bit from the impulse that we got there, as well as changing up our GNC system to reduce the impact of that effect on our navigation system. And finally, of course, those of you who've been here a lot have heard us talk about the Low Density Supersonic Accelerator project and what happened to the parachutes as part of that program. As part of Mars 2020, we went ahead and strengthened our parachute to try to combat the kind of concerns that we had coming out of LDST. And on top of that, strengthening the parachute, we also tested it at supersonic conditions out over the Atlantic from the Wallops Flight Facility as part of the Aspire program. So we took all these types of fixes and tried to make these robustness changes and improvements to MSL to make Mars 2020 much more likely to succeed. If we go to the next slide, another slide that many people have seen before, let's talk a little bit about the new capabilities that are on Mars 2020. Specifically, the top two helped us land at a place like Jezero Crater, a place really rough. Range trigger itself allowed us to shrink the landing lifts quite a bit so that we could fit into tight spots like Jezero. And of course, terrain relative navigation was critical to landing us amongst those hazards that Lori showed and that Andrew will talk about a little bit more. Todd will talk a little bit about the Medley and the results from that. Of course, we had an upgraded Medley system from MSL and with the specific addition of supersonic transducers on the forebody to give us a little bit more aero knowledge about what was going on. And of course, a whole suite of backshell instrumentation to tell us what the heating was like on the backside and of course the aero on the backside. Lori also showed you some of the pictures from the EDL cameras, which were great. And that was a new system we added for Mars 2020 to allow everybody to kind of ride along with our EDL system as we landed. Next slide. I think it's kind of a tradition, right, that no EDL talk here goes without some kind of EDL timeline. So here's how we expected the EDL of Perseverance to go. You can kind of see the major highlights that we usually have, our guided entry portion early in EDL. And then, of course, range trigger deploying our parachute at about Mach 1.75 with the target there. Getting subsonic, deploying that heat shield, firing up our six beam Ka band Doppler altimeter radar. And of course, the inclusion of TRN during this period while we're on shoot, looking for the ground and trying to figure out where we are. Doing that backshell separation, and then a divert to a nearby safe spot, which Andrew will talk about a little bit. And of course, that little crazy sky crane thing at the end and culminating with flyaway. Next slide. So I think people know how things went. I think Gregory spoiled it at the beginning that, of course, we had a good day on February 18th and things went very well. But how well did they go? Let's go to the next slide. Here's that timeline now, kind of versus our expectations and our reconstruction work so far. Now, our reconstruction work effort isn't completely done. We've got a lot of write-ups to do and a couple of small mysteries to figure out, but we think we've figured out for the most part how we've done. Generally, things that are green here are good, and you see a lot of green on this slide, which means that for the most part, EDL went largely as we expected, with very few exceptions. Generally, the exceptions, I think we have begun to understand what's going on. The only red you see on there is that the entry deceleration was a little bit lower than we expected. We think we have a handle on what happened there as well now, and of course can pin the blame on the atmosphere up high being different than we expected. But otherwise, and as sure other folks will tell you, things went pretty nominally for us throughout EDL. So now I think I just have a bunch of pictures to show that are fun, and then I'll get out of the way. So the next slide, I think Lori actually showed. You can see our parachute there as we're coming down to our Jezero crater landing site. Next slide. Instead of sticking with all the EDL camera video, which I think a lot of people saw, I grabbed a few frames from different things. Here's a frame from the Lander Vision System camera. One little fun thing that folks may not have noticed, you can see the shadow of our powered ascent vehicle up there in the top left, along with the plume disturbance that we have going on up the ground shortly before landing. Of course, after touchdown on the next slide, we caught a picture of what happened to the descent stage after flyaway. We sent it off toward the west-northwest, heading toward the delta. And you can see that cloud, that white cloud in that kind of stretched out, contrast stretched area of our HazCam picture shortly after landing, showing you the fate of that descent stage. Let's see, next picture. Here's where Perseverance landed at Butler Landing, amongst this sea of hazards that are around it. You can see our nice little white rover sitting there all on its own. Finally, some pictures of the team. I think this is the first time, especially with COVID happening, that the EDL team is really spread out all over the country between I think folks out here at JPL and at Langley and at JSC and at Ames, pretty much everywhere. So you can see us in action, and hopefully we'll be able to get together sometime soon. Next slide. Some more pictures of us post-landing. So with that, on the next slide, I just want to wrap things up and say thanks for putting up with us over the last 8 years coming to IPPW, telling you about this mission that we wanted to fly. And I want to hand it off to our next folks to tell you about the details of how everything went. Okay.
All right. Thank you, Al Chen. We do have a question from Michelle Monk. She asked, do you know what the altitude was for the image on slide 9, which I believe the LVS picture with the shadow?
Yeah, I think that's drilled out of my head in the last 3 weeks while I was on vacation, because I had figured it out a little while ago. I'll have to get back to you on that, Michelle.
Yeah, maybe just put it in the chat. And for folks on the line, feel free to ask questions, and we'll have maybe a few minutes at the end of all of the 2020 talks. So if you don't catch during the speaker talking, then feel free to just put it on there and we'll keep it in the queue. Thanks, Al. And as Andrew gets queued up here, I'm going to read his bio. Andrew E. Johnson attended undergrad at the University of Kansas, where he studied engineering physics and mathematics. In 1997, he received his PhD in robotics from Carnegie Mellon University, and then immediately started work at the Jet Propulsion Laboratory. Currently, Andrew is a principal robotics systems engineer in the guidance and control section, where he is developing technologies and flight systems for autonomous navigation and mapping during descent to planets, moons, comets, and asteroids. On March 2020, Andrew is the guidance, navigation, and control subsystem manager and the lead for the lander vision system. So Andrew, are you out there and you're ready to go?
Ready to go, Gregory.
All right, take it away. Thank you.
Sure. So, hello, everyone. This is my first time at IPPW. Thank you for having me. It's great to be here. So, I'm going to talk about terrain relative navigation. On this title slide, you see a picture taken by the Lander Vision System camera. This was taken at about 10 kilometers altitude. I really like this image because of what it shows. It shows the heat shield, of course, the delta. It also shows a lot of dust. We can see off towards the horizon. I think you're getting close to space in the upper left corner. And you really see the contribution there of the dusty atmosphere. Next slide, please. Terrain relative navigation has been mentioned quite a bit. I'll sort of give you an overview, and then we'll go into some of the flight results. So, like was said, the objective of TRN was to enable access to sites that we weren't able to access in the past. And it does this by figuring out where it is relative to hazards. The reason we wanted to do this is because places that are kind of hazardous or have cliffs and slopes and things like that also expose different layers and different types of rocks for sampling. So these hazardous sites were very interesting to the science community for sample return. And you can see there's a list of the different sites that were considered when we were doing landing site selection, and most of them required terrain relative navigation to be accessible. We ended up picking Jezero Crater, which was actually the most hazardous of all the sites, so that put a lot of pressure on terrain relative navigation to perform. You can see the landing site there in the upper right. It has been coded in color with the hazardousness of the terrain. Of course, the deltas, cliffs are very hazardous. There's some inescapable hazards there. And you can see a sort of notional trajectory coming into the ellipse and then where we actually landed within those fields of hazards. So terrain relative navigation has two components. It has the lander vision system that estimates position by matching descent images taken by this LVS camera, which was built by Malin Space Science Systems, to a map that's generated from orbital imagery. And that requires a lot of image processing, a lot of data processing. So to do this function, we also had to build a high-performance computer that was specifically designed for image processing called the Vision Compute Element. Those image landmark matches are fused with IMU data to generate a complete state estimate. It estimates position, velocity, and attitude. Really, what we needed to estimate was position, but those other pieces of state information are in there. Allows us to get a better estimate of position by also estimating those quantities. So once the lander vision system estimates position, it's provided to safe target selection, which uses that position estimate to figure out where it is relative to a hazard map, and then it picks a safe landing site that also avoids the back shell. You can kind of see those wedges there drawn on the map. It has to pick a site within those, and then the existing MSL, EDL, G, and C takes us down to that landing site. And part of the development, as Al mentioned, was to make sure that we do no harm to MSL, EDL. Even if TRN happened to not perform, that you could actually kill velocity above the surface and touch down. increasing your chances of safety. All right, so next slide, please. Okay, I'm going to show this movie, but before it plays, I just want to talk a little bit about what's going on here. There's a lot. So in the upper right is the LCAM image, and you're going to see it change. Then the other two images are the map that we're matching to. And the lower right is the full map, which is 30 by 30 kilometers. And that blue box in there is a cropped region that's about 12 kilometers across that we figure out on the fly using the spacecraft position estimate that's provided to the lander vision system. And then we match within that blue box. The red curving thing is the footprint of the image. And now you can play the movie. So we initially do a coarse matching mode where we match like a few large features. That takes out the large position error. And then we go into, the LVS goes into a fine matching mode where it matches up to 150 landmarks that are smaller across the whole field of view. In this video, the colors correspond to whether something's an inlier, meaning correct, deemed correct by the system, or an outlier. And green and blue are inliers, and the other colors are outliers. Here we're descending on, we descended on the parachute through the image sequence, and now we're doing the divert to go to the safe landing site. So the footprint has gotten smaller, and you can see that the attitude of the vehicle is changing, which corresponds to the different off-nadir looks that happen during the powered descent phase. Okay, going on to the next slide. Next slide. Okay, how did LVS do? Here are some plots of the position, velocity, and attitude errors with some epochs identified. So time 0 is when image processing starts. That happens about 4,200 meters. Prior to that, we're just waiting for that altitude. There's a coarse mode, which does most of the correction in the position estimate. That's that big sort of cliff in the position error. These are errors, so this is a deviation from what we believe is our best estimate of the true trajectory of the vehicle. The cyan line is the start of backshell separation. So prior to that is when we provided a position estimate to safe target selection. And then there was a bonus where we did the landmark matching during the powered descent phase, and to just see if it would work, and it did work. It worked all the way down to 500 meters, at which point the system had a parameter to stop processing images, and so the system stopped at 500 meters. So we got at position errors that were much less than our 40-meter requirement. Attitude errors, there's a typo on this page. It's actually attitude errors are less than 0.1 degrees. And you see that in the Y channel, there looks to be a constant chain attitude error, and that's most likely due to a misalignment between the camera, which is on the rover, and the IMU, which is on the descent stage. We're still looking into that. And the velocity errors were less than 1 meters per second. Next slide. This is safe target selection flight performance. So you can see in the diagram there that you see the trajectory. This is an overhead view. You can see the places where the different LVS position estimates were generated, and the one that was actually used by safe target selection identified. What happens next is that the safe target selection system places wedges on this safe target map, and within those wedges, it needs to decide where is the safest place to land. So behind that is a color image where blue is the safest and red is the least safe. There's 2 wedges, and the reason there's wedges is because the system has to not only identify a safe place to land, to touch down that avoids hazards, but also avoid the backshell, which probably is going in the direction that you've been traveling. So the system ran. It picked identified sites within the wedges. It always goes to the safest site, and that site happened to be in what's called the reverse wedge. It had a safety level of 1.35%, and that's where the vehicle diverted to. There was another safe site in the primary wedge, but it wasn't as safe at 1.9%. And finally, the red triangle is where the system would have gone if it had done an MSL-style divert, 300 meters to the side, and that had about a 20% chance of landing risk, so more hazardous. Worked great, and we ended up actually drifting on the parachute away from the delta, and then the divert took us even farther away from the delta. So the rover right now is driving like mad to get back over to the delta. Let's see, next slide. Okay, so summary. It worked great. 5 stars is what we like to say. The LVS system converged on the first fine image number 4. That's as fast as it can converge. It matched nearly the maximum number of landmarks from 4,200 meters all the way to 500 meters, which included power descent, which was this bonus. The system selected the safest location possible in the wedges, and you can see that in the color picture there. There's a zoom in on the hazard map superimposed on, I believe, an EDL cam image showing where the hazards are and then where we landed. It landed surrounded by hazards, but not on hazards. And we landed within 5 meters from the targeted location. And in order to do that, all kinds of things had to be done really well. The LVS position estimate had to be very accurate. The hazard map had to be a very accurate representation of the truth. You know, this is something we're doing from orbit, and we don't have ground truth. So excellent job there. And then the nav filter propagation, many things involved with that had to be very accurate as well. So in summary, TRN worked great on Mars 2020, and it's being used in planning a Mars sample return lander. And there's also, of course, many other potential future missions that could use it. Thank you.
All right. Thank you, Andrew. Any questions for Andrew regarding TRN?
Here's the team. And here's the people that funded us. Forgot to say that. Very important piece.
That's right. There you go.
Yeah, big team. Lots of different funding sources.
So Andrew, I'll ask you a question. Throughout kind of, I guess, the life of TRN, you know, I'm guessing the most fulfilling moment was it working on Mars. But if you were to choose a moment in time that was most challenging, I guess, what would you say in terms of the development and of TRN?
The most challenging was actually getting it to be baselined on the mission. That was, I think, once we achieved that, which required, thanks Al, yeah. Once we got, the project was convinced it was low risk, and the scientists had to make a very strong statement about needing it, because it wasn't in the original plan for Mars 2020. And then people that wanted it needed to provide extra funding because it wasn't in the plan. And so all of these non-engineering pieces had to come together. I mean, well, the risk reduction was done actually earlier, and then getting it baselined came down to a need and funding. So I think that really went well. People recognized the need, and the money was provided, and then we were able to be successful. And now we have this for all these future missions. It's a great thing.
Awesome. Thank you for that insight, Andrew. All right. No other questions. Thank you so much. And we are now going to queue up Todd. So as we're queuing up Todd White, I'm going to read his profile or bio. Todd White is a member of the NASA Ames Entry Systems and Vehicle Development Branch and is the Medley 2 Principal Investigator. He has contributed to many space missions and proposals, including Shuttle, Orion, OSIRIS-REx, InSight, MSL, Medley, and the current Mars Sample Return Earth Entry Vehicle. Fun fact, his favorite practical application of temperature measurements and ceramic insulators is for creating Memphis-style barbecue. Todd, are you on the line?
I am. Can you hear me?
Yes, we can. Thank you.
Okay, great. Thanks for that introduction, Gregory. So yeah, let's go ahead and talk about the instrumentation that was operational on the heat shield and back shell during entry for Mars 2020. And go ahead into the next chart if you like. So there's a lot of really great imagery that came out of the Mars 2020 landing. Obviously, landing a rover on the surface is pretty important too.
So I thought I'd point out here, Al showed this before with some of the nominal values for how entry went. And I just want to point out the phase in which Medley 2 is operational. So Medley 2, as I'll talk about in just a moment, is what makes the temperature measurements and the pressure measurements on the front and the back of the aeroshell. And Medley 2 is much like Medley was on MSL, is operational for about 10 minutes. And Medley 2 gets powered on prior to cruise stage separation. So I'll be talking and showing some of the information that we got during entry from Medley 2, but there's actually a set of data that comes before that is the well that we have. It's actually pretty cool. We're able to see things like shock events from the cruise stage separation. We can actually see the sun as the vehicle is rotating at a time. Before starting entry. And then, of course, we're gathering data all the way down through up until the point where the parachute gets deployed. But as soon as the heat shield gets ejected, Medley 2 is no longer operational because, as you'll see, that's where our avionics and our brains reside, is on that heat shield. So there's a period of time where there's overlap between the EVL cameras and Medley 2. But I'm the most thankful for those EVL cameras. Of course, they're great, but I love getting to see the Medley 2 hardware as it's flying away. So go ahead to the next chart. We'll take a look at what this hardware looks like before the aeroshell was integrated. So Medley 2, as we've said, has sensors on both the front and the back of the vehicle. So in the background there on the left, you can see the tiled Pika heat shield. And if you look really closely at this great PR photo, you can see small circular regions, which are the instrumented TPS plugs on the front of the vehicle. And there's a total of 11 of those on the heat shield. And if you look even closer, in some cases you can actually see the small holes that are drilled for the pressure taps. And there's a series of 7 of those, and those holes are feeding to mostly the supersonic pressure transducers, ranged for that, but also a hypersonic pressure transducer. And in some cases, you've got the hypersonic and the supersonic right next to each other. And then on the right, you can see the back shell of the vehicle. And this is a little bit easier to see our sensors because the camera's closer, but also because we don't have any of the thermal control paint right next to our sensors. So you can see there's some instrumented thermal plugs. That's the circle with the red around it, the RTV agent that holds it in place. And then towards the individual wearing the bunny suit there, you can see we've got a radiometer, a heat flux sensor, as well as a TPS plug, instrumented TPS plug right next to each other. And we've also got a backshell pressure transducer, which is the first time for NASA to do that on a Mars mission since Viking. So that's what it looked like before integration around the rover and before launch. So let's take a look at what it looks like on the way down to Mars. Go to the next chart, please. So great images. This is a fun one immediately after heat shield separation. And so you're looking now at the back of the heat shield. Over there on the right, you can see the black box. It's about the size of a chunky 1990s laptop, is what I think of it. It's that's the electronics and the sensor support electronics for Medley 2. And then you can see the orange wiring. That's the instrument harnessing for Medley 2 going from that electronics to our sensors. And you can see from the back side what the pressure transducers look like. I've also got it highlighted. It's a bit harder to see, but the wires that run through the heat shield and go to the thermocouples in our TPS plugs. Okay, so let's go to the next chart. So I covered a lot of this already, but MSL Medley had 3 major hardware components. The system that's responsible for measuring pressure is MEADS, or the Mars Entry Atmospheric Data System. And that's, again, the hypersonic ranged and the supersonic ranged pressure transducers on the heat shield, as well as a backshell, really low pressure sensor, a single one there. And then on the heat shield, it's the thermal instrumentation system. It's MISP, and that's a series of thermocouple embedded in TPS plugs installed across the heat shield. And they're also installed at 6 locations on the back. And then we've also got a few dedicated direct heat flux sensing sensors, a radiometer and a heat flux sensor. And then, of course, all of that feeds into the sensor support electronics, or the SSE, which is really a high accuracy multiplexing analog interface that also can talk to the DPAM to provide our information there. So Medley 2 doesn't store any of our data. It's all stored by the rover and then telemetered back. Let's go on to the next chart. I won't spend too much time here. I think we've shown this sort of thing before, but this is where those sensors are actually located. So on the heat shields, those red dots are where we have our thermal measurements, and those are scattered to try to get the best overall heating footprint and to try to pick up on things like turbulent transition. And then the pressure transducers are optimized such that we can back out the vehicle orientation using those pressure measurements. It's almost like a flush air data system. And on the back shell, we placed sensors scattered around again to try to get at heating. We picked the location of that supersonic pressure transducer to get good measurements back there, and that was really informed by some ballistic range testing we did. Go on to the next chart if you like. This is the fun list of all of the actual science channels that we got. Most of what we measured was at around 8 hertz. In some cases, we had data channels that were a bit higher than that. And then we did decide on a subset of these channels that we wanted to have come back in a live data stream at about 1 hertz on the off chance that there was some issue with entry that we wanted to try to understand. So I've got those highlighted in red there. So the things we really wanted to understand, stagnation pressure, as well as turbulence on the heat shield and back shell. So all that said, let's take a look at what we actually got. Next chart. So for the pressure, this is the Meade system. I'm showing both the heat shield and the back shell here. So in the upper left-hand corner, you can see, and this is time from TNAV in it. The hypersonic pressure pulse, that's the one in blue, goes up nice, very close to what we would have predicted for the hypersonic pressure pulse at the stagnation point. Not terribly surprising, we flew something that looks a lot like a nominal trajectory. You can also see the supersonic pressure transducers there, which due to the scale don't look all that impressive, but in fact they are. Those are ranged such that we are getting really good measurements after about 660 or 670 seconds on the way back down supersonically. But as you can see, we're also able to get signal prior to the hypersonic pressure pulse, which means we're able to get pressure measurements to inform upper atmosphere as well. If you look way at the end on those at around 780 or so seconds, you can see where the ballast masks are fired, and you can also see where where we're on parachute for a while. And on the bottom left there, you can see the backshell pressure measurement, which has also turned out pretty good. For all the cases, the in-flight zeros that we got on these were as expected and consistent. And Chris Krelgar and our team has already done trajectory and atmosphere reconstruction using the Mars 2020 INU data, all of our data, as well as stuff from MCE and Meta. And I think we can say right now that the reconstructed atmosphere from that is showing higher densities at above 50, 60 kilometers, which is consistent with what we saw in Mars 2020 GNC. So that's pressure. Let's go on to the next set. Next slide, please. So this is temperatures that we measured during entry. These are all of the heat shield temperature channels. What we can see already is we didn't lose any of these, which means we know we didn't have heat shield recession greater than 75 thousandths of an inch. We also didn't max out any of these temperatures. And I can say that for the stagnation temperatures here, MTH01, those are the solid green line, that our predictions pre-entry were somewhere between 800 and 900 degrees Celsius. So they're very consistent with what we measured there. And we expected things to be higher at the turbulent regions. And so we see that as well. The other really cool thing here is we can look at this and immediately see flow field transition occurring. If you just take the flat up derivative of the data, you can see slope changes. So that's pretty cool. We're able to see other sort of fun effects that aren't often in our models, but we know are happening, such as water phase transition. So you go to the next slide, we'll take a look at the back of the vehicle. So again, those temperatures. So these are temperatures about 1/10 of an inch from the surface, most of them. As you can see, less than 250 degrees Celsius. The cool thing here is we were clearly able to pick up radiative heating being as the dominant source of heating for the highest location. As you can see down there in the bottom right-hand corner, this is using an inverse estimation with our ablator models, some work done by Ann Alpert and Malad Mazari. And we're able to see there that the total combined heat flux there are consistent with our design predictions that we would have had on the order of 5 watts per centimeter squared back there. So overall, this data is looking really good, and it's already allowing us to say that Mars 2020 performed pretty well, and certainly in terms of aerodynamics and aerodynamics and TPS. If you go to the next slide, I'll wrap this up. So we were able to pick up what we were looking for. The sensors that we got from MSL Medley, so hypersonic and thermocouples and the heat shield, all worked well. We were able to pick up flow field transition. The new sensors that we flew worked really well. I didn't have enough time to go to the radiometer and heat flux sensors, but we were able to confirm the phenomena we were interested in did show up. No noise in any of our sensors. So we're very thankful to Mars 2020 for the ride and to the entire Medley 2 team across Langley, Ames, JPL, and Lockheed Martin. And take some questions now if you like.
All right. Thank you, Todd. Maybe we'll get to one or two questions here. I see that you've had support from Chris answering in real time.
Oh, thank you, Chris.
So we'll try to do one or two, and then maybe you can answer the rest offline via chat. So maybe easy one. Florence can ask, what is the estimated temperature at the surface?
Yeah, that's a good question. We're talking about peak surface temperatures. And I want to say we're on the order of, I don't have it here. Hang on. Yeah, I'll just say we're on the order of 12 or 1300 degrees Celsius, I think. And there's a fair amount of uncertainty, and that, of course, changes. We're not always at those sort of temperatures, but that would be sort of the peak ones that people think about.
Okay, thank you. And we'll do one more quick one, and then the rest I'd hope you'd answer via chat. From Jill's, phenolic compounds present in the SLA 561 have, for some of them, a melting point as low as 313.6 K. Even in the backshell, our experiments show that there will be some deposit on windows or metallic surfaces, even on the backshell. How do you manage those?
Yeah, that's a great question. It's an area of continuing research. We have characterized that in ground testing and observed that the effect of those kind of components that we get, ablation products and stuff for the paint and everything else, that does strongly affect our radiometer. It does not appear to strongly affect our heat flux sensor. And so what we have is characterization of what those ablation products do in terms of blocking the CO2 wavelength that we're likely to see. So we do see ablation product blockage. And part of that is what helps us is we've got several different types of sensors that can all observe different aspects of the same thing. So yeah, it's a combination of ground testing, simulation, and relying on our multiple data sources to come up with the best estimate overall for what heating was and what the sources of it were.
All right. Thank you again, Todd, and the Medley 2 team. Todd, if you can go ahead and scroll through the questions, that'd be great, and answer them. Yep. We'll transition now to Paul, talking about GNC. Thanks to all the presenters so far who have been sticking on time. That is helping us a lot with the schedule. All right. So Dr. Paul B. Brugaroles has an Ingeniero Superior Electrico degree from Universidad de Nevada, Spain, and an MS and PhD degrees from USC. He joined JPL in 1997 and has worked on R&D, GNC for small bodies, precision pointing for space coronagraphs, and flight projects, SRTM, Cassini, Spitzer, MSL, and Mars 2020. Paul is the Mars 2020 GNC Chief Engineer. Take it away, Paul.
Thank you, Gregory. All right, so let's talk a little bit about GNC and preliminary reconstruction. So if you go to the next slide. So let's just get a quick reminder about the hardware that we use for GNC, basically the sensors and the actuators. So for EDL, after we separate the cruise stage, there are two key pieces of hardware which are balance masses that are used to introduce a CG offset. You can see the entry balance masses in the back shell. The cruise balance masses are in the opposite side. You cannot see them. For navigating, we use a descent IMU. We also have a prime and a backup. We use the prime for EDL. And also we have a landing radar. This is a Ka band radar with 6 pencil beam antennas, and you can see it in the diagram there. And for control, during entry, we use descent thrusters. We have 4 clusters, 2 thrusters each. During the exatmospheric phase, we use them in a blowdown mode with a thrust about 175 newtons. And during entry, they go into a regulated mode, and we get a thrust of 250 newtons each. And then for power flight, we use the landing engines. We have 8 and these are throttable engines that could produce a range from 500 to 3,200 newtons each. And last but not least, there is a lander vision system camera. It's hard to see, but it's basically mounted in the belly of the rover, and it's pointed over there that Andrew talked about. So now let's go to the next slide. So this is actually the software, the GNC software is going to land us. And I just want to quickly give a good reminder of the functions. So we have a navigation filter that's going to basically blend the IMU and the radar data to give us a full estimate. During entry, we have an entry guidance system. This is, we continue the collaboration with JSC from MSL. So we work with Lynn McGrew and Brian Kellen and Gavin with that. And then the entry controller basically will basically implement the bank commands that guidance will create. And then on the power flight, basically we have the whole heritage system from MSL. This is what Guru created and what Jordy took over for 2020, that basically will do 6 DOF guidance. There's trajectory profilers, and then there is both positions and attitude controllers to achieve that. And in blue at the bottom, you can see the addition of the software needed to be added to EDL GNC to do the safe target selection. The map relative localization, as Andrew mentioned, was provided by the LBS system, but the STS had to be implemented within the Heritage EDL GNC software. Now, to make this work, as Andrew mentioned, is that we had to tune the system to basically don't increase risk for MSL. And a key thing here was having enough fuel, and luckily we had enough left over from MSL. And the second part was making sure that we optimize that divert to be able to achieve the larger divers. MSL had been designed to do a 300-meter divert. We wanted to go all the way to roughly 700. So we had to basically increase the backshell separation to enable to basically have a graceful power descent in terms of timeline margins, in terms of nadir angles of the radar, saturation of the engine. So that was the key part of the tuning. So let's go next. As we mentioned some of the new things, but there was also a couple of things that we had to fix. One is something that I'll refer at the beginning, which was the parachute-induced mortar. The parachute-induced, as the mortar comes out, there's snatch forces that are from the confluence fitting and the sabot that create a very large disturbance that excites that panel where the IMU is mounted. So we end up having to change actually the IMU, the output resolution of the IMU by a parameter change, because we were concerned actually of saturating due to this high frequency vibration that could saturate the sensor. And the other thing we had to do is basically mitigate, as I'll mention, the MSL plasma velocity anomaly. So we did that by adding a local gravity correction and also by tuning the nav filter to basically filter out bad radar measurements. So now let's go to the next slide. On this slide, this is a visualization of the flight telemetry. It's a long visualization, so we're going to skip over some periods of time. So let's start it, and I'll start talking. So on the left, you can actually see the GNC modes. And you can see the dials at the bottom will show altitude, Mach, speed, acceleration, and fuel use. So at the beginning, what you see is we separate from the cruise stage where it's a spinner, so it's turning at 12 degrees per second. We have to de-spin. But before we de-spin, we fire these warm-up pulses that what we do is we fire one thruster on each pair to warm up the engines. You can see here actually the spin down, and after the spin down is complete, we basically do the turn to entry. Basically, the vehicle is now set itself up to the attitude that we want at the entry interface. And now we're going to hold that attitude during the exo-atmospheric phase for roughly 9 minutes until we get to entry and basically doing a very gentle attitude dead banding. So now let's actually, if you could help me skip until 9:57. So now we're jumping right before, this is actually where guidance started. Basically, the way that guidance starts is basically we have a G trigger. When we get to 0.2 air Gs, guidance starts. This actually happened a little earlier than in our predictions. It turned out that our models were not very accurate, atmospheric models were not very accurate at high altitude. So we actually, we sensed an atmosphere was denser on Mars than what we had expected. So we started guidance early, and what these did is entry guidance computed an initial bank command that told us that we needed to be 40 degrees off of our predicted bank, and we started a little bit of a slew. But soon after, when we start sensing the denser atmosphere, all that got corrected, and the software handled that very gracefully. As part of entry guidance, the vehicle does range control to correct for downrange errors. While doing that, it's going to do band reversals to correct for cross-range errors, same as MSL. And then when we get to 1100 meters per second, we'll get to basically heading alignment to basically aim for the landing side and maintain altitude. And once we get to heading alignment, basically we're going to be waiting for the range trigger. This was a change from MSL. MSL opened the parachute based on a velocity trigger. What we're going to do for 2020 is opening downrange, so this allows us to get a lot smaller errors in downrange and basically reduce our landing ellipse of roughly by a factor of 2. So if we now jump to basically 1247, that's actually going to be the time for the parachute deploy. Is when we do as I mentioned, this is the range trigger. While we do the range trigger, we're going to do two things. One, we're going to slew the spacecraft to do a 180-degree rotation, such that when we eject from the backshell, the radar beams are pointing towards the landing side. And we're also ejecting at this time the ballast masses to remove the CG offset right before we open the parachute. You can see here that the parachute was open. And you can see here a little bit of the rest mode of the spacecraft under the parachute. So this is as the parachute is decelerating. And what we're going to be doing next is basically ejecting the heat shield and basically, you can see here the heat shield was ejected. We turn on the radar. This is the pointing of the radar beams. We have the 6 pencil beams. One is a nadir beam. There are 3 at 20 degrees, and there are 2 what we call the sky crane beams that are used for the sky crane that are at 55 degrees. So at this point is when the nav filter tries to acquire the ground for the first time, and we acquired it roughly at 7,500 meters over the ground, a little lower than MSL, but still very good performance and providing good landing timeline margin. Now, if we could jump to 1441, this is we'll keep descending on the parachute, but now basically when TRN came to play. Here you can see the footprint of the LCAM image on the ground, and this is where the map relative localization, as Andrew was showing, is figuring out where we're at. And this is what is going to be used by the safe target selection to do the divert. So now you saw that basically we had the back shell separated. Now basically you don't see the LCAM image anymore because we're actually not using it for GNC. We still use the radar beams. You can see as we do the divert maneuver, and now we basically we're now performing the divert. And because the thrusters are fixed, basically the vehicle has to tilt to achieve that roughly 600 meter divert that we needed to do to get to the safe target location. Now we go to the vertical phase. The vertical phase is basically where we allow the system to correct for altitude errors. In flight, we basically we had an allocation of 130 meters, plus and minus 130 meters to correct. We actually only used 5 of those meters. Actually, we knew the altitude very well. And we got a little lucky that as we drifted of the delta, it was very flat, so we had a very good knowledge of the altitude, so we didn't need that much constant velocity according capability. You can see here we landed. That's the pixel we landed, and now as you zoom now, you can actually see the wedges plotted on the ground and the landing location. So this was kind of the landing, and if we go to the next slide quickly, I'll give you a few more fun facts of the landing. Okay, so I think I mentioned most of these. Let me just quickly. This is something that Andrew mentioned, but it was actually very impressive. We were very surprised. So the nav filter gets initialized from on orbit with the EDL parameter update, which was basically a few hours right before EDL. We did that Wednesday evening. And that knowledge basically gets propagated to the ground. Actually, and then when the map relative localization is going to tell us how much in error we are. It turned out that the error in the nav filter was only 127 meters. Our models predicted to be in something in the order of 3 kilometers. So we actually did outstanding in this area. And the other thing to mention here is range trigger worked pretty well. We basically landed 1.7 kilometers from the center of the ellipse. And our ellipse was 16 by 14, so it's pretty within 1 sigma. And the other fun fact here I want to mention is that the other thing we were concerned was about those radar plume interactions that basically we have seen in MSL that pebbles will basically create errors in the landing radar that will then impact the performance of the nav filter as we were touching down. In MSL, we basically violated our horizontal velocity requirement. For 2020, we retuned the system to basically do a more stringent filtering, and actually we saw it working in flight. It basically edited out 5 measurements that actually exceeded 0.2 meter per second threshold, and we're pretty happy. We're actually still finishing the construction, but the initial assessment looked like it did work very well. A couple other things we have noticed on the reconstructed telemetries, we have seen a little bit of an overperformance on the landing engines in the order of 3%. And our fuel use is pretty much in family with expectations. One last thing is that if people are interested in more the details of the GNC reconstruction, we're going to have in the order of a dozen papers at the AAS Astrophysics Specialist Conference in Agos in Dickinson, Montana. It's a virtual conference. So if you're interested, you might want to go there and you will get to see all the details about the GNC system and all the plots about all the control errors and all the details.
Awesome. Thank you. Thank you, Paul. Since we're running a little late on time, if you guys have questions for Paul, please put them in the chat. And I just want to double check before I introduce Ian. Ian, can you hear us?
Yeah, can you guys hear me okay?
Yeah, we can. Okay, we're working some technical difficulties, but we'll get through it here. All right, so we're moving on to the last part of our 2020 section here, which is the parachute. And Ian, for those of you who do not know, he was the principal investigator for LDSC and for Aspire. And fun fact, Ian swallowed a nickel in first grade and once ran over a common ground snake, which is the second most venomous land snake, while cycling through the bush country of Victoria, Australia. So Ian, why don't you go ahead and take it away? I hope you can see your slides.
Yeah, no, I see it great. We can jump, well, first I'll acknowledge the other folks who've contributed heavily to this work, Chris Galgard, I see online, Clara O'Farrell, and Chloe Sack here as well. And there's a whole team of others, but just with regards to the content in these slides, I'd say these are the 4 main contributors. Next slide, please. Go ahead and show the video. Let's play it a couple times, and I'll kind of talk through. Hopefully this shows up well enough over WebEx. Looks like it's pausing a little bit there. A little bit of background on the parachute itself. It was a 21.5 meter nominal diameter disc gap band parachute. Geometrically, the design was very, very similar to the same design that we used for the Mars Science Laboratory parachute. Predominant changes included use of a new broadcloth material. It's a custom weave nylon that was roughly 2.5 to 3 times stronger than the material we used on MSL. At only about 50% increase in mass, and also an increase in strength in the suspension system, the suspension lines and the radials, moving to a higher strength Technora material. See if you can play it a little bit more. Again, it doesn't seem like it's coming through very smoothly for me. Folks who maybe have seen this, it's available on YouTube. You can find it quite easily. Main things I'll point out, in general, the deployment looked very nominal for us. Prior to flying this parachute at Mars, we did test it both subsonically and supersonically at Earth. We acquired a ton of excellent data, a lot of good imagery watching it inflate supersonically. Comparing the videos that we have from the Earth testing to what we've seen here with the Mars video, this looks even better. The parachute pack is moving exactly as we'd expect. At line stretch, there's some rotation. It's about orthogonal, but it quickly corrects itself, and the parachute seems to emerge rather cleanly. And then the inflation of the parachute itself is remarkably uniform. Not any significant area oscillations that we can tell. In general, the parachute seems quite stable for the supersonic conditions at which it was deployed at. If you go to the next slide, I pulled a couple stills just to talk through a couple aspects. The top left image is taken nearly immediately after mortar fire. You see the parachute lid, the large black circular section. The parachute pack is the cylinder that's pushing that lid further back. Sliding out at about 7:30 on that is a little piece of insulation that goes between the lid and the parachute pack. That was very predicted, something that is extremely light. We thought about trying to retain it on the pack, ultimately selected not to. So the fact that that was moving off was entirely anticipated. In the lower left of the image is a little piece of the parachute lid called the radome that covers the parachute low gain antenna. Back on MSL, we had done some mortar testing and noticed that that could break free. We had applied some fixes, which we hadn't tested until actually, at least tested on Earth, until the beginning of the Mars 2020 project. We took one of the MSL lids, went and tested it and saw that the radome stayed attached. Convinced ourselves that we had a pretty good fix there, and then here we see that it's actually detached from the rest of the lid. Not a problem in and of itself, just something that was unexpected. Little pieces of debris, very expected, associated with the mortar lid and the mortar deployment. Nothing that we really concerned ourselves too much with. The image in the top right shows the lid rotating and starting to move orthogonal off. The pack there is about at line stretch. You see the canopy beginning to emerge from the parachute pack in that 90-degree rough orientation. If you looked a few frames after that, you would see the pack correctly reoriented itself. A couple stills from the inflation sequence itself in the bottom region. The first time that we see the vent, it is very circular. That indicates that we have very nice, symmetric, uniform loading across the inflating disc portion of the canopy there. If you take the projected outline of this parachute and track it over time, you see that it is remarkably circular throughout nearly the entire inflation, or at least as far as supersonic parachute inflations can go. Very clean, very uniform. Doesn't look like we had any significant entanglements or otherwise regions of the parachute that stalled. Generally a very classic supersonic DGB inflation, where the disc begins inflating very quickly, develops a nice uniform geometry, and then the band begins moving radially outwards until you have roughly full inflation in that lower right image. Let's go to the next slide. In terms of the conditions at which we deployed the parachute, lots of numbers here. Folks can look at these offline. The middle three columns there are associated with the last predicted Monte Carlo runs that we had done. The column highlighted in blue is our current best prediction of the as-flown conditions, and then I've provided the MSL deployment conditions on the far right for comparison. So at the time of mortar fire, we were about 10 kilometers above the surface at a Mach number of 1.81. So very similar to MSL 1.72, pretty much right down the middle of our predictions. Dynamic pressure of about 520 pascals, also pretty much right down the middle of our predictions, a little higher than MSL's, but not significantly so. And then angle of attack at the time of mortar fire was slightly lower, but 1.9 degrees is quite modest. Line stretch conditions and full inflation conditions, but I'm not going to talk too much about those. Let's go to the next slide. In terms of the timing, again, some numbers here. The main thing I'll point out, inflation from going from line stretch to full inflation based on the load was about 0.63 seconds. That's about 5 milliseconds different than MSL, despite being slightly different velocity conditions, but otherwise pretty much right down the line of predictions. Supersonic flight from full inflation to Mach 1, total of about 7.5 seconds there. Next slide. Looking at the reconstructed loads, calling out a few events. So from the bottom, you see this is time for mortar fire. Line stretch took about 1 second. You see a little rise in force associated with the line stretch, essentially a change in suspension lines coming out of the bag to the parachute coming in the bag creates a higher tension force that you can measure in the deceleration of the vehicle. And then you see the very rapid parachute inflation. Peak load was about 34,000 pounds. Again, pretty much right down the middle of predictions. You notice the very rapid rise in inflation load, again, something very typical. The drop-off, some small little increase, about 1.75 seconds after mortar fire before it comes back. to about at 2.25 seconds after mortar fire. But otherwise, other than the typical peak load, decrease, rebound, very minor oscillations throughout, very low frequency content here, very low amplitude oscillations. And then otherwise, you're just looking at a steady decrease in drag associated with the change in dynamic pressure. Next slide. If we back out the total force coefficient, here we're comparing the reconstructed value for Mars 2020 with the MSL model and the MSL reconstruction. A couple things noticed here. One, in general, the model does an excellent job of capturing the range of total force coefficient that we see, with the exception of one area right around transonic. Going back to the Viking program, there's data to suggest the presence of what's referred to as the drag bucket, a sharp decrease in the drag of the parachute around Mach 0.9 or so. That's been present in our models. Our recent Mars parachute reconstruction, though, going from Phoenix, MSL, InSight, and 2020, all indicate that we have yet to observe this in flight at Mars. And so it's likely a conservative aspect to the model there. Otherwise, one of the other features that stands out is just, even though the values themselves seem offset between Mars 2020 and MSL, it's remarkable that some of the frequency is still present there. The peaks and valleys, if you will, are almost on top of each other with regards to the Mach number.
Ian, please wrap up in like a minute or so? Thanks.
Yep, almost done. Next slide. Looking at the parachute pull force data, in the video, if you saw it real time, you'd see how stable the parachute seemed to be. We can back out the angle at which the parachute was pulling on the air shell. And these are all very, very small values, typically, always less than 5 degrees, generally in the 1 to 3 degree range. Very, very stable parachute overall. Next slide. And I think this is the last one. Just looking at the rates and comparing those to Mars Science Laboratory. On MSL, we saw rates just under about 70 degrees per second that occurred a few seconds after peak inflation. On Mars 2020, the peak rates were within about a second or so after peak inflation, and they were a bit lower, about 45 degrees per second. And then they damped out relatively quickly after that and stayed relatively low until we achieved heat shield separation. Not a whole lot to glean necessarily from this. This is probably a bit of a roll of the dice in terms of the initial condition in which the parachute was inflated, the angle of attack. 2020 did have a little higher inertia than MSL, but I don't think that would have been a significant contributor. Next slide. And that was it. We've got a ton of phenomenal imagery, but it's always, nice to see the context of the inflated parachute with the landing site in the background. And so this is one of the high-rise images of the Mars 2020 inflated parachute descending towards the surface there at Jezero.
All right. Thank you, Ian. In order to respect the break a little bit, I think we have one question or two questions in the chat. So if you can answer that, Ian, before you leave, that'd be great. Otherwise, everyone, this concludes the Mars 2020 section of our session. Thank you again to all of our speakers. Let's give them a virtual round of applause. And the plan is to be back, or please be back here at 10 a.m. Pacific. We will do the poster Q&A. If you have not seen them, please go watch the posters and have questions ready. So with that, we will be back in 12 minutes or so. Thank you, everyone. Are people raising their hands? Is that what that sound is about? Jill, we will not be sharing the videos during the break, but people should go watch them if they have not yet already. Hey, John Thornton, just FYI, we can see your video. I don't know if that's on purpose or not, but yep.
Thank you.
No problem. I enjoy seeing people on camera anyway, but I wasn't sure if that was on purpose for you. All right, everyone, we are approaching 10 o'clock. I hope everyone's stretched out, had bio breaks. I'm just going to pretend I'm talking to myself.
We're here, Gregory. I had a good snack.
Great, I see that. Galactic Lucky Charms, that's a thing now. And Nitro Cold Brew, okay.
Yeah, man. Sugar and caffeine. Let's keep going.
All right, let's get some virtual reactions just because I like making people do things. Welcome back, everyone. So the next 10 minutes is dedicated to the Q&A portion of our poster, for our posters. So I hope you guys watch some of the posters. Let's get them in the chat, and I hope all of our poster presenters are on the line to answer these questions. Let's see. If we don't get a question in the next 30 seconds, we will go to some of our stock questions. Here we go. Question for, okay. So question from Manuel Dominguez Kumar. I believe it's for James Maurice. Both the Pika and Pika-N models slightly overpredict the temperatures of the MIST-2 flight data. What do you think may be the main reason for this overprediction? Jeremy, are you on the line?
Can you hear me?
Yes, I can hear you.
Hi, everybody. So that question from Manuel. The main reason for that for us is the environment. Here we used a fully turbulent environment. So we have like other results like in other papers where you see the difference between laminar and fully turbulent, and you see that probably the regime for the MSN entries transition between those two.
Okay, thank you. Tim, do you mind putting this in slideshow? Thank you so much. All right, another question for Jeremy. How does the cooler temperature of pika-N affect the performance of the heat shield? And does the asymmetric coating after parts of it are bladed off cause any localized heating of concern?
So, I mean, usually when you do sizing for TPS, you're looking at the bond line temperature. So if you have a cooler temperature at the surface, you're gonna have a cooler temperature at the bond line. So that's a good thing. So that's interesting because at the beginning, NuSil was like just for spread of the dust, but it looks like it has a beneficial impact when you enter the atmosphere, lowering the recession rates and the surface temperature. And so here for the model that we give, it's still like a first model, so it's not long that we're studying that new material. It's pretty complex. So we did a bunch of assumptions for that, and for here we don't see any removal of the NuSil during the entry, even when we do fully turbulent, which is probably like higher heating that we expect. So we don't see any asymmetric coating removal.
Awesome. Thank you very much. All right, more questions here for Carolina. Are you on the line, Carolina?
Yes.
Okay. How would your thrust force be implemented? What would its magnitude be?
So the thrust force, so we was modeled as we assume a gimbal angle positioned on the payload, and it was basically a free vector. And the magnitude constraints were between 400 Newton to 1,000 Newton. So that's where the constraint, and then the optimal thrust command, so the vector was computed by the successive convexification.
Thank you.
Thank you. I'm going to move on here to another question. I believe it's for Kieran Montgomery. Are you on the line, Kieran?
Yes, I'm here. Can you hear me?
Yeah. How are or will you validate your computational models and simulations?
Oh, perfect. Thank you for the question. And thanks everyone for inviting me. We are planning to look into doing experiments at Imperial College as well. We've got the model. We'd like to develop the model and, look at these different thrust coefficients and different diameters. So we're hopefully going to compare those to our computational methods. We have done some experimental validation before as well with cases without the jet. And if you'd like to see those, I can show them. If you want to email me or message me in the chat, I can forward them.
Thank you. And sorry, to set more context, I should start saying this, but Kieran was working on supersonic retropropulsion for Mars EDL and their computational models. Okay, we're going to move on to for Jonathan Bustani towards supersonic parachute inflation capabilities within the launch, ascent, and vehicle aerodynamics framework, LAVA. Are you there, Jonathan?
Yes, I'm here.
All right. What were the challenges in beginning to develop models for supersonic inflation, since this was kind of a new thing post LVS, right?
Right. It's the hardest part is not necessarily individually the structure or the fluid, which I mean both pose a lot of challenges. It's really the efficient coupling between them from like a computational point of view. You typically have like two independent modularized solvers unless you knew you were going to do fluid structure interaction in the first place. So you have almost two different codes that need to communicate efficiently. And so the computational challenges dealing with very thin geometries, undergoing very large displacements, and communicating between the two solvers is very hard. And so before you can really even get into any of the physical modeling challenges, the computational challenges are, I would say, some of the hardest initially.
Awesome. Thank you. All right, we're going to move on to Amal Sahai for dust particle aeroheating calculations for Mars entry hypersonic flows. And the question for Amal is, maybe possible at some point that the high temperatures in the boundary layer soften the dust particles so that collisions between particles become inelastic.
Hi everyone, thank you for this opportunity to present my work. That's a great question. So right now I just prescribe a fixed value for the coefficient of restitution, but at some point I can actually start looking at these, just to begin with, simple formulations where that coefficient restitution depends on the temperature of the particle. And so then we can probably capture that effect. Like you start with cold, hard particles that are more elastic, and then eventually you move on to warmer, more gooey particles that tend to stick together or undergo inelastic collisions. But yeah, that's a really interesting observation.
Okay, thank you, Amal. All right, moving on to Stanley for Martian microprobe EDL system. Stanley, I hope you're on the line. I see two questions here. One is, are the parachute and airbag masses included in your mass estimation? And question two, what deceleration do you expect upon touchdown, and how do you estimate this value? If we have Stanley on. Actually, I don't see Stanley online, so might have to skip that. All right, let's see. Any other questions that I missed? Oh, for Jeremy? All right, so question for Jeremy. How equilibrium assumptions versus kinetic limitations could affect the thermal matching results and ablation model?
So it's part of like a big assumption that you're doing is the equilibrium. It's going to be part of like a future work, so it's pretty hard to answer that without doing the work. But future work will include finite rate chemistry, and at the moment we model as like a pure silica, and so we can also try like other condensed species at the surface.
Okay, thank you. Let's see. I think this is for Carolina again. What's the landing velocity sensitivity to the timing of the final thruster? Oh, I lost it. Thruster. If it's late, do you stall?
So at the time where the thrust is turning on, the glider has a pretty high velocity. We carried several simulations with different wind conditions, and the velocity were all within from 15 meters per second to 50 meters per second. So we actually we carried a different simulation with all this within this range to see if the thruster was able to compensate for those. So within this range, it was still possible to land at zero velocity. I mean, close to zero velocity. But we never simulated a stall. So.
Great, thank you, Carolina. Okay, moving on to John Thornton for analysis of the MSL medley entry data with coupled CFD and material response. We have two questions for you, John. One, do you expect a significant change in the results once a non-zero char blowing rate is considered? And two, how long does it take for the coupled model to converge?
So yes, I would expect a significant change in the results. The reason we're not including char blowing is just basically to sort of establish a process and then
include char blowing once we've done that. And then it takes, so for how long does it take for the coupled model to converge? So usually it takes 3 to 4 iterations of each of the Deepler and material response Pato codes before convergence.
Awesome, thank you. Do we have any other questions for our poster presenters? As I continue to throw up my virtual reactions. All right, we have one question for Carolina. What do you think could be the advantages in terms of EDL performance of the glider with respect to retro propulsion?
So one of the advantages could be that the system is lighter and it has a high maneuverability. So, and also from a cost point of view, to be less expensive. But we never went into too much detail in that direction. But that would be the major advantages.
Awesome, thank you, Carolina. Another question for Jeremy. Your poster showed results for MISP-2. Do you expect similar for other locations?
So we expect always the nozzle to be like lower temperature. I picked the MISP because it's the highest temperature that we have, and we expect like the highest heating from like the environment. But yeah, we expect a second of the everywhere on the heat shield.
All right. Thank you for all your questions. I think I captured or asked all of them, and we're about a minute away from our next set of invited speakers. So if I missed anything, please send them back in the chat, and I'm hoping the presenters can answer them. But with that, I'm going to hand it over to my co-session chair, Oscar, to introduce our next speaker. Oscar,
thanks, Gregory.
Okay, you're welcome.
Our next speaker is Sanjay. So it's a pleasure to introduce Sanjay Diadran. He is the Mars Strategy Team Leader and Future Mars Studies Coordinator in the Directorate of Human and Robotic Exploration at the European Space Agency. He has worked in the area of Mars exploration since 2003, contributing to payloads and performing flight operations on the NASA Phoenix Mars mission, and since 2009 has been at ESA in the Future Mars program, preparing technologies and mission designs for future European missions post-ExoMars. He was the ESA campaign lead for the Mars Sample Return program, shepherding it from the early discussions with NASA in 2016 until it was successfully confirmed as a joint ESA-NASA program in 2020. Sanjay has since transitioned from MSR to planning for ESA's future Mars exploration activities.
Thank you very much for the introduction. Thank you very much for the introduction, Oscar, and thank you to the IPPW organizers for inviting me to share ESA's current perspective on our future Mars exploration plans at this meeting. I'm very glad to have this opportunity to attend the IPPW, which is one of the most interesting Mars exploration conferences annually. So what I'm going to share with you today is really hot off the press. ESA has been in the process of developing its future Mars, future exploration strategy for all 3 destinations, LEO, Moon, and Mars, over the last 6 to 9 months. And we're not complete with that yet. However, we wanted to have the opportunity to share our work in progress with our stakeholders, including the community like yourselves, on where we're heading so that we can bring you along with the process and even get feedback from you about our thoughts that can help define and fine-tune our approach before we finalize it by this time next year. So do bear that in mind when you hear about what I have to say, that none of it is cast in stone today, but this is at least the direction that we think we need to go. So next slide, please. One of the first things related to this that has happened recently is that we've had a change of Director General at ESA. So we had Josef Asbacher join us as the DG of ESA 3 months ago, around the same time as NASA had a new administrator as well. And the DG has issued this document for ESA Agenda 2025, which lays out his vision for ESA over the next 5 years in particular, but also over the longer term. And we in the Exploration Directorate at ESA are very pleased to see that the exploration program and exploration activities are taking very much a visible role in the DG's agenda for all of ESA in the future. And in a number of places, exploration activities are mentioned, including expansion of our activities in LEO around the 2025 timeframe, but also looking forward towards what we're going to do after the ISS gets retired into the 2030s. We also have an ambition to, in lunar exploration, to finally achieve the goal of having a European on the surface of the moon in the 2030 timeframe. And so that's something that we are hoping our activities as we ramp up in lunar orbit and eventually in the lunar surface in the 2020s will help us achieve that ambition by 2030. And then for Mars exploration, clearly the human exploration of Mars has been a long-term goal for ESA exploration program for a long time and continues to be a vision in the 2040 timeframe as indicated in the DG's agenda. So exploration is very much at the heart of where our new Director General wants to take it. Next slide, please. So I'm showing you this slide, which is a screenshot from Bill Nelson's hearing at the House on Capitol Hill in May, where he showed this picture of the Chinese Zhurong Mars lander on the surface of Mars rover on the surface of Mars, really giving the message that here is another space power in exploration that has reached a level that is approaching on par with the great space powers of the world, especially in the areas of exploration. And so there is a space race of sorts going on in the field of exploration, and this is clear evidence that that is the case. And Europe now has to think about where it is going to place itself in this new race for the future. Next slide, please. So this slide is showing how we see the activities, the main activities in recent times and going ahead at the three destinations from the main international powers in space exploration, which are the US at NASA and now China as well. And we can see in LEO there's been a move towards the commercial developments of transportation to LEO and services to the ISS, but also for other applications that are growing. And the Chinese similarly have also put up their new space station only recently and having astronauts on board right now and doing space walks. So there's definitely a catching up by the Chinese that has been rapid and is coming on par with the other players. Similarly, at the moon, there's will be a huge increase in activity expected from the US in the 2020s, but as well from China. They've demonstrated a lot of capability with even a lunar sample return and now developing heavy launches to take humans out towards the moon as well in the 2030 timeframe. And then finally at Mars, we've seen Perseverance landing this year and the Chinese rover as well, and the US and indeed ESA are planning a Mars sample return mission towards the end of the decade. But similarly, China also has ambitions in that direction. So clearly, there is this acceleration in activities between the US and China. If you click ahead, there's a plan for permanent presence at LEO from both of these players, permanent presence at the moon as well, sustainable long-term presence, and for Mars, all of these activities are heading towards a human Mars mission in the long term. You could click forward a couple, please. So now, and again, yes. ESA is in the position of in its strategy work asking itself, in this new and accelerating framework internationally, where shall we place ourselves as a global space power and exploration in the next 10 to 20 years? So our answer to that is this new program called Terra Novae, stands for New Worlds, and this is intended to be a single exploration vision for the three destinations of Leo, Moon, and Mars. And just to recall, at ESA, we have all of those three destinations under a single directorate. So it's human and robotic. Leo, Moon, and Mars are gathered in a single program, with each destination supporting the other with the long-term goal of European participation in human exploration of Mars. Look forward, please. So looking at where we are today and where we would like to go in terms of guiding our development of the strategy, we can see in the 2020 to 2030 period in the coming decade, we are already establishing quite a significant role in exploration in three destinations in terms of having mutual interdependence with our main partners. In this case, NASA being our main partner in all of these three destinations for ISS, for the Gateway, for Mars Sample Return, and we also have Roscosmos as a key partner in the ExoMars program. So in all of these programs, ESA has a critical role to play, but we are mutually independent, so we rely on our partners significantly to enable our roles, and they rely on us as well. But as we move towards the next decade, 2030 onwards, we see the need for increased level of European autonomy, increased level of capabilities that we can offer to European needs as well as the international partners to be able to explore all of these destinations. So, for example, at LEO, we see the need for a European platform and potentially even the capability for sending Europeans into low Earth orbit with our own systems. Similarly, at the Moon, we see a need for increased ESA-led missions, European-led missions, where partnerships will be certainly part of that, but not only relying fully on partnerships as we've done in the past. And finally, for the Mars destination, similarly there, big missions as well as other classes of missions being more European-led, while still keeping the door open to partnerships and eventually expecting to play a significant role in an international human Mars exploration mission at the end of the 2030s. So this move towards from interdependence towards more European-led capabilities is very much driving our strategic thinking for all three destinations and Mars as well. Clicking forward, please. So this is going to give you a quick look at the synergies that we see between all the three destinations. And again, we want to synergize our activities and our technologies and capabilities at all three destinations in order to allow and make maximum use of our capabilities. So if you just click forward to show all the lines here, starting with low Earth orbit, a platform for science and habitation, for continuing our research in low Earth orbit, but also to use as a platform for testing new capabilities for the Moon and Mars. And we see synergies in transit vehicles between Earth and lunar orbit, as well as from Earth or Moon to Mars as an area for synergy. If you keep clicking forward through here, there's other clear areas like precision landing on the Moon, and similarly at Mars with ISRO, deep drilling, nuclear power capabilities, comms and nav. All of these things are transferable very much from lunar to Mars exploration, and we intend to synergize and our strategy in order to maximize our use and feed forward capabilities from these destinations. Next, please. So what are the key roles that we're looking at as we think about what the future Mars strategy should be in the 2030s? Again, I mentioned autonomy as being an autonomous provider for having capability to land on our own, to be able to provide a comms and nav service. These sorts of things are important for us to have as roles in the future. but also being a partner of choice, showing credibility in our ability to deliver on programs where we are in partnership, so that we are a go-to partner of choice for the future is a key aspect of that. And as well as continuing our scientific and technological leadership in key areas of Mars exploration from our heritage missions of ExoMars and Mars sample return that's coming. We want to expand on that and go further in the next decade as well. So all those capabilities in the central box there will help us, if developed, achieve these four key roles of the future program. Next, please. So this comes down to my last slide, which is I'm sure what you've been waiting for. What is our plan for the next decade? Where these are going after Mars sample return? So we have a lot of heritage to build on from planetary missions as well as Mars exploration missions of the past, and we want to reuse this for the future. But we also have a need to expand that capability to push the envelope, ultimately to be able to play critical roles in the human surface exploration of Mars in the far future. So these missions that we are planning in the 2030s, robotic precursor missions, are intended to be gathering the science that we need to close knowledge gaps, as well as develop the capabilities technologically in order to play those critical roles in the future. So starting from the bottom and going around to clockwise around the planet, we see a need for a series of small and fast missions in the future to be able to test new technologies, but also to increase the cadence of missions so that we are able to do complementary science to the large strategic missions. And then on the strategic level, there are three key areas: climate, network, resource extraction, the ice on the surface of Mars, as well as astrobiology, advancement, and ExoMars are three themes that we are going to be exploring with surface missions. So particularly the landed climate network mission is intended to involve a number of landers. And so we see a large number of EDL missions coming up for Europe in the future to really solidify our capability in this area. Finally, leading to a human exploration journey, if you click forward, together with international partners at the end of the next decade, going from the Earth, using our capabilities and to the moon, eventually to the surface of Mars. Thank you very much. And I'm happy to take some questions.
Thank you, Sanjay. I think we're slightly out of our time limit, but I can see a quick question on the chat from Davide Bonetti. He says, slide 6 showed an inflatable heat shield image under European-led capabilities as robotic precursor for 2030-2040. Also linked to large payload precision landing on slide 7. Is there a pre-decisional plan to have this technology for Mars tested by ESA?
We see that as beneficial for providing capability to support human exploration missions of the future. So in our current planning, we would see a mission towards the end of the 2030s as the opportunity to demonstrate such advanced EDL capabilities once we have secured conventional EDL capabilities early in the 2030s.
Okay. Thank you, Sanjay. I think we have to move on. Our next presenter. So,
thank you. Thanks, Oscar and Sanjay. That was excellent. We're going to have our final invited speaker now. Our speaker is Dr. Zach Putnam. Zach is an assistant professor in aerospace engineering at University of Illinois at Urbana-Champaign. Dr. Putnam leads the research group focused on mission design and analysis for space and hypersonic systems. He earned his PhD in aerospace engineering from Georgia Tech and was previously a member of the technical staff at Draper Laboratory. He was handpicked as a participant in the Keck Institute of Space Studies workshop on revolutionizing access to the Mars surface, and he's here today to provide us with a description of that activity. Take it away, Zach.
Thanks, Michelle. I'd like to know at some point which hand actually picked me. It's really a pleasure to be here today. It's nice to see so many familiar names on the participant list. I'm looking forward to when we can all get together again in person at some point, and hopefully the not too far future. Anyways, as Michelle mentioned, I was fortunate enough to be asked to participate in this workshop, Revolution Access to the Martian Surface, which is hosted by the W.M. Keck Institute for Space Studies. And I want to be real clear about my role here. The workshop really is led by Chris Colbert, Abby Freeman, and Bethany Elbin. I am today just a presenter, just giving a status update. I think we thought this was something that the IPPW community would be interested in. Yeah, so if I go to the next slide. So when we say revolutionizing access to the Martian surface, really this is focused on smaller science-driven missions as opposed to the big monolithic human Mars missions. And the primary motivation here is if you look at science goals documents, and there's more than one out there. I've got a shot here from the MASWIG report from November of last year. If you look at the goals, many of them require in situ access. Basically, we need to be on the surface. And so lots and lots of key science goals, you can only do it in situ. And on top of that, a lot of them really benefit from having some kind of surface mobility system, right? And you can imagine, right, there's sort of two ways to get access to those things, right? We could land lots of landers, or we could land one lander with a mobility system, et cetera, and that depends on what kind of science you're going after. And if you look at this chart here too, you can see that not only are lots of these goals, not only do lots of them require surface access, but you can see the surface access ones that I've highlighted here in pink also tend to be more on the expensive side, right? If you look at the top, there's small spacecraft, Discovery class, New Frontiers, and then flagship on the far right. There's basically nothing with the dark blue box that achieves all the priority science on the small spacecraft stuff. So if we think about and take as a given that we need to get to the surface to answer these key science questions, next slide, please. We can come up with a few questions. One is, can we fit PI-competed surface missions into, or more of these, into Discovery or small spacecraft kind of cost cap mission classes, and including the mobility system on top of that? Right now, that's not really been the case. And in order to get there, can we leverage some other things that are going on both within the Mars community as well as outside of that to improve our ability to get these kind of payloads to the surface to answer these science questions? In particular, number 2 here, can we leverage some of the approaches used in small sats and use that to improve surface access? And then in a different vein, can we leverage different programmatic vehicles and things like CLPS, the commercial lunar payload services, where NASA in particular is basically trying to create a market and then relying on somebody else, commercial providers, to get payloads to the surface of the moon? Could something like that be beneficial to Mars exploration and helping us answer these science questions? Next slide, please. So that's really the genesis of this workshop, right? How can we leverage some of these new things happening to reduce the cost associated with getting these scientific missions to Mars, right? When we say revolutionize, we're really talking about increasing the number and making surface access easier, which roughly translates to lowering the cost at some point. And so we had 3 primary goals for the workshop. One is trying to identify what the most important measurements are related to science questions in the decadal survey, and sort of what kind of technology platforms are required to achieve those measurements. Also looking at different architectures and technologies, from EDL to mobility systems, that would allow us to do efficient operation of multiple Mars assets that get us either the surface access or the mobility that the science questions require. And then lastly, like I just mentioned, how we can leverage small satellite approaches and say commercial lunar payload capabilities to help break down the cost mass dependency of Mars surface missions, right, and lower that price point, which, in theory, would enable us to send a lot more missions. Let's see, am I doing on time? Let's go on to the next slide. So when you think about the science, and we spent some time on going through all these goals, and there's other goal documents that we talked about. When we think about sort of three high-level areas, atmospheric science, geology, and geophysics that we're interested in at Mars, they have sort of specific in situ science measurement needs. For example, for the atmosphere, one of the things we're most interested in is measurements in the lowest scale height of the atmosphere, so closest to the surface. And that's something we generally can't do from orbit. And so we have to be on the surface for that. And in addition to that, there is value in getting concurrent measurements at multiple locations in terms of studying the atmosphere and studying dust storm formation and these sorts of things. On the geology side, there's a real need for both local and regional scale measurements. And in particular, as we've seen with existing rover systems, right, we get a lot of benefit in terms of providing comparison across different areas if we can provide a long traverse, right, that's consistent with having some kind of a long duration mobility system. And then on the geophysics side, there's a need for multiple landing sites, like some kind of a network, think seismometers, to locate seismic events, and then also mobility for those systems as well. And if you put all this together, the reality is that we need not like a couple of landers, we need lots of landers and or mobility systems to actually address all these high priority science goals, and across multiple science disciplines. Next slide, please. So one of the things we did, the workshop started in late March, early April of this year. And one of the first things we did was try to identify some of the, quote, tall tent poles that are barriers to lowering costs. And we looked at cultural and programmatic things as well as things on the technology side. And I was looking at this list this morning, actually, and we basically wrote down everything. Almost everything is an issue, right? You know, those of you that work in EDL and these things, right, all of these things are connected to each other. So, you know, things we'd like to do are, you know, on the cultural side, right, you know, there's the biggest thing that always comes up is the current community risk posture, right? We don't like to fail for obvious reasons. The missions are expensive, right? So if we can lower the cost and make failure okay and things like that, right, that'd be a huge opportunity. And on the technology side, there's real room for improvement in EDL systems, service mobility systems, improving payload size, weight, and power, and then also on the manufacturing and assembly, test, and launch side. Next slide. So I was going to talk a little bit more about EDL systems and cost, but we're running a little bit short on time, so I'll do this really quick. But basically, the current, because EDL is sort of my area of expertise, the current paradigm right now is that every single EDL system we build, to a large extent, is bespoke, right? It's designed, it's custom for a specific mission, specific science objectives, specific requirements, and that makes it pretty expensive. So some options for reducing EDL costs, I see I've got a character snafu there. You know, things you could do are like eliminating subsystems. For instance, if you don't carry a landing system and can tolerate a hard landing, right, that can save you mass and costs and things like that. And then the other one I want to highlight is block buys and builds, right? Maybe we you know, do more than one of these. Not a build to print 10 years later when it's hard to do, but a build to print right away. We build a whole bunch at the same time, that kind of thing. And there's contributions that EDL could make to overall mission cost reduction and things like that too. Next slide. So we've got a few more things going on with the workshop that'll continue through this year. We've put together 4 study groups looking at some high priority areas. 1, programmatic changes to the Mars exploration program. 2, the quote culture club, looking at potential changes to the culture of how we do these sorts of things. And then 3 and 4, a little more on the technical side, looking at could we do a mobility mission, service mobility mission for $200 million or less, and then also looking at some architecture trade studies for small network landers. And our second meeting, hopefully in person, will be in September, and there'll be a final report to follow that. Next slide. And so I just want to acknowledge the WM Keck Institute for Space Studies for hosting and putting together the workshop, and then all the other participants that I'm representing here. There's 31 of us. It's really been fabulous to interact with these people across. It's a pretty good cross-section of industry, government, academia. It's really been a lot of fun. So thanks very much.
Thanks so much, Zach. I think this is a really interesting topic for our community to consider, so thanks for bringing awareness of this activity. And there'll be a final report when our second workshop concludes. So we're going to move on. If you have any questions or comments for Zach, please continue to chat. We're going to move on to our oral speakers, and Oscar is going to introduce the next couple. So take it away, Oscar.
Okay, thanks, Michelle. Also, thanks to the speakers of the invited talk. So we'll start with the 6 oral talks now. The first 2 will be on ESA's ExoMars mission 2016 and 2022, respectively, and then we'll move on to future mission studies. The first talk will be given by Bart Van Ho, who holds a Master in Engineering and a Postmaster in Experimental Hypersonics from the von Karman Institute of Fluid Dynamics. He has done his PhD at the Royal Observatory of Belgium on the ESA Schiaparelli missions. He's currently working at Deimos Space as atmospheric flight engineer. Some key results from the PhD are presented here. His PhD defense is scheduled for public defense on the 7th of December. So go ahead, Bart.
Thank you, Oscar. I'm very happy to be here today. This is a culmination of 10 years of work, so I would be happy to talk for 10 hours. Unfortunately, I can't, so I will try to do my best. Leave some time for questions. Next slide. This was ExoMars Schiaparelli. It was Europe's second attempt to land on Mars, and unfortunately didn't make it all the way. It made a hard landing, as it's called sometimes, which actually happened at 500 kilometers an hour, so it was definitely very, very hard. On the upside, there were many measurements taken on the way down. And this is the first European mission and the only European mission with flight data. So my job in the Amelia team, which was assigned by ESA, mostly made up of engineers and scientists, my task was to look at the data set and reconstruct the trajectory and the atmospheric conditions. So we just saw an excellent example of how that's done with Mars 2020 and MEDLEY 2. MEDLEY 2 was a set of experimental sensors, including pressure, temperature, and heat flux on the heat shields, front and back. Schiaparelli had something similar and was actually the first Mars mission with sensors on the back shell. The one I will be focusing on are the flush air data system sensors, so the 4 pressure sensors on the heat shield that you see on the bottom right there. And the goal, ideally, this is another reconstruction we did for InSight on the left, is to obtain really quality and high-resolution images of the atmosphere during EDL. Next slide. This is a brief review of the data we're using, the problems with existing work. So on the top left is the idea. There is an IMU, accelerometers, and gyroscopes inside the vehicle. This can reconstruct the trajectory. The pressure sensors on the heat shield can observe the atmosphere and also the direction of the oncoming flow, so the angle of attack and side slip. What I'll be using in this work is the IMU, the FADS, and the radar. The radar also gives good information about the trajectory, but only operates at the end of the EDL. So in the bottom left is a figure that tries to summarize what are the issues with the Schiaparelli dataset. Basically, it is a big puzzle. There are pieces missing. So there was a radio blackout during entry. There is no data there. There was more than usual uncertainty at the entry interface point because Schiaparelli was not guided and tracked really until the moment of EDL. It spent 2 or 3 days in sleep mode before arriving at Mars. There is no landing data, obviously, because there was the crash landing. And the reason the mission failed was the parachute deployment dynamics caused the lander to swing faster than the gyroscope could measure. It saturated. So there are issues with the data there. Also, the FADS measurements, which were unique and first of a kind, first ever for a ballistic Mars entry, they didn't live up to their calibration precision. So many, many little problems that together make it a very big problem to find out exactly what happens in flight. The bottom figure is where things stood until last year, I would say. So these are different reconstructions of one simulation in green, the simulation, but the other are reconstructions of the angle of attack during entry. So you see there's a gap where the blackout occurred. That's about 1 minute. The bottom axis is time. The yellow dots are FADS measurements that have been analyzed, but clearly were not that accurate as intended. The black line is the best estimate we got based on acceleration ratios and the aerodynamic model of the angle of attack, and it matched pretty well with the simulation. The other curves that have these oscillations going on, those oscillations are not aerodynamic, and we suspect that there was probably an error in the trajectory and specifically the initial state. Now, there were other things that were a bit mysterious in the post-flight. Right after the mission, for example, the atmospheric density was up to 20% high after the blackout in the only other existing reconstruction. It's cited there, Abu Dham. This is also Amelia's work, but the first iteration. Today we present the second. Next slide. So to sum it up, our objectives are to make a comprehensive reconstruction using IMU radar and FADS. I will introduce a new method, not new in the world, but new for EDL, batch least squares fitting to improve the trajectory reconstruction. We will have a close look at the atmosphere and at the FADS. There's another little novelty there, a method that I propose to deal with the blackout. You can ask questions about that. I will not have much time for it now. Next slide. So the batch least squares basically repeats the IMU trajectory reconstruction, trying different initial states. The additional information we need to improve the initial state, we take from those acceleration ratios, or I call them the aero database, the ADB flow angles. So the green things on that figure on the left, top left, are constraints. There is a forward IMU integration, which improves the initial state until the flow angles from the IMU and the ADB acceleration ratios line up. There is one piece of information needed to get a good entry trajectory, and that is the altitude at parachute deployment. So ideally, if the data set was intact, we could process everything, but now I split entry and descent phases to only use altitude at parachute deployment from a reverse IMU reconstruction, again with the batch least squares method. But this time fitted were constrained by radar measurements, and the radar data were beam ranges and terrain relative velocity. That was really a nice thing that Step Rally had that helped the descent phase reconstruction a lot. So I focus on the entry phase, and the two phases are loosely coupled to avoid low quality IMU data, mostly due to the saturation after deployment. The blackout bridging method is based on onboard recorded trajectory data. So that measures a kind of relative trajectory change that you can use to come up with good polynomial interpolations for the blackout. Again, there's no time to go into details. The new thing about this methodology is the batch least squares, which usually Kalman filters are used. Kalman filters, they walk along the trajectory, they march across it, and at every point they try to consolidate an estimate of the trajectory with other constraints. The batch least squares looks at everything at once, and the idea was that this would be good in the presence of bias errors or linking information down the road with things that happened much earlier, in this case, the initial state. I want to spend some time explaining exactly what this is because there are some experts in the room. There will be a paper coming out later this year. Next slide. The results from this were really promising. The green line on these figures left velocity and altitude on the right. The green line is the previous reconstruction using an extended Kalman filter. The red line and its uncertainty bounds is very close to this. The method is flexible because you can incorporate any sensor model or estimate any parameter. And again, versus Kalman filters, you don't have to linearize or prepare this in any special ways. The price is just computational. I'm repeating many reconstructions and making least squares fit, and that process is repeated in a Monte Carlo. The altitude and velocity were consistent with what came before, also Bonetti, which was the post-flight simulations. Next slide. The new thing are the flow angles, because these were not accurately reconstructed before, remember. So I'm showing them after the blackout on the big figure. Before the blackout, they are less mysterious and also reconstructed well. Just a little picture to show we have that. But the ones after the blackout here, so the red lines, they are really the results that we worked for. The black line were the ADB constraints. The red line is the final result now. The uncertainty bars are much reduced. The blue bars were for the ADB angles, and those are mostly due to aerodynamic uncertainty, also the IMU. So the final results are way more accurate. They don't yet include the FADS. There is a curiosity between 130 and 150 seconds. And this is the this little zigzag is the final remnant of the spinning artifacts, the rolling motion artifacts that I called out before, those oscillations in flow angles. They're related to the spin rate. And they're mostly removed, but these remain. And if we go to the next slide, we moved on to atmosphere reconstruction, and we will actually use those flow angle observations. So first, I'm showing the density on the left. The red line is reconstructed density versus the models that were used to design the mission, Mars Climate Database. So if we look at all the conditions, also temperature in the middle and pressure not shown, average dust conditions are favored by the reconstruction. This was also consistent with what came before. What's new are the Mars climate sounded retrievals, shown bottom right. These happen to fill in the blackout data gap and provide really strong confidence in the temperature reconstruction. There was a mysterious thing happening in the temperature profile before parachute deployment, what looked like a strong inversion, but it could in fact also be a headwind. So if you go to the next slide, here we show the temperature reconstruction in red on the left with a big inversion. Now, if instead you assume there was a headwind, but what all this is based on is a dynamic pressure increase. And this is real. It was measured by the IMU and the FADS. What's not sure is if it is a headwind, and there could be other wind components, but we could see only headwind along track, or a temperature inversion. Neither are really expected there. This is far above the boundary layer of Mars. If it was a wind, it is consistent with the model prediction range and would reach about 50 meters a second, as shown at the bottom. It's the first time such a signal, and it's a very strong one, is seen in an EDL data set. I think it's curious. So we kind of consider the two extreme cases there. You can go to the next slide because time is running out quickly. Remember the flow angle zigzag that remains, so we can remove that as well by assuming a wind. And I'm not just so in love with winds because that's what the FADS is actually for, and I'm reading the tea leaves. We tried many things to remove these artifacts, and in the end, the wind was the only thing that would work. This wind also fits within the model prediction range, reaching about 15 meters a second. Is predominantly a north wind. And so both of these wind observations are reasonably solid and made without a FADS or even or the acceleration ratio method. So there's maybe something about spinning probes that inject certain types of errors in the reconstruction that have the spin rate, and therefore become visible. And instead of errors or sensor errors, these can also be wind velocity fields. Let's go to the final slide. This is FADS methodology we prepared with DLR, pressure modeling. We assume CFD, equilibrium thermochemistry. I showed this at an earlier IPW. Let's move on. We're nearing the conclusions. So everything I've shown has been based on IMU and radar. A lot could be done. Surprising amounts of information could be extracted from those. Sadly, the pressure sensors did not work that well. The center one was blocked. And we eventually found out that one of the three remaining ones also performed beyond its sigma calibration range. So that was unfortunate. Still, there are interesting things to be seen in the residuals after fitting the CFD model with the data. As I said, we assumed equilibrium chemistry. There are some residuals there after the blackout, bottom left of the screen with the orange arrow, and those are likely then non-equilibrium flow observation. So moving on to the final slide. We've managed to squeeze the data set like a lemon and got more information from the Schiaparelli data, meaning flow angles and a refined atmosphere reconstruction, possible wind estimates during the entry phase without using FADS data, so that's something I think nobody expected. I think the vehicle spinning motion is worth to investigate more, and there have been other missions, NASA missions, that have used spin stabilization. I really want to look at those further, maybe apply the least squares method there as well. We should also make a more broad and theoretical study of the advantages or the pros and cons between Kalman filters and least squares. I would say least squares is more of a post-flight approach where you have the whole data set and you have time to process it, whereas Kalman filters can also be used for guidance. The Schiaparelli FADS, was severely limited by a lack of rigor, I would say personally. We certainly have seen how to do it better with MSL, and also the other sensors like COMARS on the back shell of Schiaparelli, they worked really well. And what this study really has done is provided a better trajectory reference and more curious observations for other studies, other sensors that were present on Schiaparelli to be updated, extended, repeated, and so on. Thanks for your time. I would love to answer a question, but I'll do it later if there's no more time. Thanks.
Yeah, thanks, Bart. I think we have to move on. There is a questions, but I'll suggest you reply on the chat. So our next speaker is Francesca, and it's a pleasure to introduce her. She's the PI of Amelia EDL Science Experiment of the ESA ExoMars project. She was the deputy PI for the ASI instrument on the ESA Huygens probe of the NASA ASI ESA Cassini mission. She's been studying planetary atmosphere and Martian dust levels by in-situ measurements, and she took part of several in-situ mission proposals and studies. The floor is yours, Francesca.
Okay, thank you. Okay, Amelia is an experiment based on assessing the local atmospheric science and surface landing sites using the ADLS sensors. Despite the failure of Schiaparelli, we managed to get some flight data that help us to investigate the anomalies that determinate the unsuccess of the landing, and also some data from Amelia has been showed by Bart. And we have the same experiment on ExoMars 2022, and we plan to put this expertise and lesson learned in perspective for the ExoMars 2022. Next slide, please. And Schiaparelli, as I mentioned, it was the descent model technological demonstration from the European side, and it was took by the TGO, the ExoMars 2016 mission. The Trace orbiter was delivered in the ballistic trajectory to Mars, and next he arrived 3 days after hibernation. He arrived at the entry point of the atmosphere of Mars. Next, and continued the hypersonic atmospheric entered under an instrumented shield. Next, and then the descent phase was under passive parachute. This should be followed by a proximity phase with the thruster activation controlled by the radar Doppler altimeter, and then it should have been there should have been a soft landing on crashable structure. The parachute opens nominally, but unexpected dynamics at the opening of the parachute caused the GNC anomaly that resulting in a wrong altitude estimation, and therefore the parachute and backhover were separated earlier than foreseen. The retro rockets were fired only for 6 seconds and prematurely shut down, so that starting from an altitude of 3.6 kilometers, the Schiaparelli was in free fall. So next, please, next one also. We lost the signal. Next again. We lost the signal on 1 minute in advance, actually, and the probe was crashing on the surface. Next. Okay. So next one, although the mission didn't succeed to land and we didn't get the data transmitted back, Schiaparelli was transmitting the data to the TGO during all the phase of the entry and descent, and also the carrier signal was recorded by the ExoMars Mars Express, the ESA Mars Express orbiter, and also from the direct link to the ground from the GRIT meter wave radio telescope in India. So here we can see that the Doppler tracking was Schiaparelli by TGO, and we see in comparison with the simulation, and we clearly see all the events from the entry entry interface point, the starting of the plasma blackout, and the end of plasma blackout, and the parachute opening, the front shield release, the back shell separation, the disactivation of the retro rockets, and the loss of the signal 1 minute before in advance with respect to the foreseen landing because of the impact. Next, nevertheless, as mentioned, it was possible to reconstruct from the ADL flight data. It was possible to reconstruct the trajectory and the attitude of the probe, coping with the problems of limited data set, but also with the gap due to the data due to the transmission loss. And here we can see the work by Budan et al. In 2018 that it's the ground track of the Schiaparelli on the Mars surface. Actually, that was the reconstruction was done by the inverse integration of the GNC estimates actually, and also with the data simulation by Kalman filter with the radar data, and also matching the impact point of the different elements. And as you can see, also the hook shape of the ground track, and also the location of the back shell. It's on the surface. It's an indication also is compliant with a wind that starting from at the altitude of 9 kilometers was blowing southwest. Also, beside the trajectory of the attitude, the atmospheric profile being retrieved, the atmospheric density is proportional to the drag. So the deceleration measurements were used in order to derive the density profile, and pressure was computed starting from the hydrostatic equilibrium, and then temperature from the low, the ideal gas low. So next, so we are ready to put our experience and lesson learned in ExoMars 2022. Schiaparelli, as mentioned, was a European technological demonstration of entering a center landing. Up to the parachute deployment, it should be say that it was demonstrated, not the landing, of course. The ExoMars 2022, the descent module, will contain the surface platform and the rover. So there will be a ballistic entry, but the entry in the descent sequence will be a little bit more complex due to the fact of the dimension of and the size and the mass of the probe itself. And also they will follow with the radar activation and thruster activation and propulsion by retro rockets to get the soft landing. So next we get the comparison of the two probes. Actually, as you can see, the dimensions are quite different. We have the frontshield diameter of Schiaparelli ADM was 2.4 meters. And ExoMars 2022 has 3.8 meters, and also the mass is almost the 3 times, so 4 times almost. Next, also next graph. Okay, we have also to slow down the ADM, the descent module of 2022. We need 2 main parachutes, each of which has its own pilot chute for extraction. And there will be a first stage main parachute of the dimension of 50 meters that will be open at supersonic velocity, and to slow down the probe while it's plunging in the atmosphere of Mars. And the second stage will be 35 meter dimension. It will be open when at subsonic velocity. Next, in order to validate all the system qualification, several experiments have been planned and are performed. We have in which there are full-scale low and altitude deployment sequence tests by drop from helicopter and or balloon. Following their success, the test of 2019, 2014, 2020, The parachute was an adjustment and testing on the parachute and some modification. Also, there was the need of this dynamic test in order to testing the deployment, and this was done in collaboration with JPL. We had images on the right, the high-speed extraction test. And next, on the 24 and the 26 and 24 and 25 of July, there was the first high altitude drop test from Kiruna that was successful. So the deployment sequence was tested with success, and the probe was decelerated, and parachute and probe next parachute and probe has been recovered in good state. So as for the previous mission, Amelia will reconstruct the trajectory of the ODM and will retrieve the atmospheric objective profile basing of the GNC measurement performed by two inertial measurement units and the radar altimeter, so mainly from the acceleration and the gyro rates. And plus there will be also some measurement that will be performed by the surface platform, which namely are the Meteo package that is foreseen to make ADL phase measurement in the deceleration, angular velocity, and also direct pressure and temperature measurement when the front shield will be released, and also the TSPP imaging system that will image the landing site during the descent. And of course, there will be also the radio link communication between the ADM and the radio receiver on board the Mars orbiter, and also for direct Earth that could be used in order to derive the properties of the atmosphere. Next. So the approach will be starting from modeling the entry and descent model, the dynamics of the sensor and the dynamic of the sense model, starting from the entry, a personic entry with different models, with dynamical models, and also of the probe during the descent under the parachute. So we are performing simulation, and then there will be combination of data with the reconstruction for data simulation, so kind of filtering as we have done for or other methods. So different approach, method, and data set are applied for cross-check and validation to retrieve the most accurate atmospheric profile. Next. The ideal is to exploiting the ADLS measurement for scientific investigation of the atmosphere and surface, and this will be done in reconstructing by a theoretical procedure the attitude and trajectory, and also combining with dynamical models, and also with the near time reconstruction using the DL communication link. While with remote sensing and observation and descent imaging, and also the ground tracker, will be possible to the characterization of the landing site and assessment of geomorphology and surface characteristics. Another component of another skills within the EMEA team is the expertise in atmospheric modeling and data simulation, and it is a key importance for prediction and also for scientific interpretation, mainly to get the forecast prediction of the condition and the context of the ADL condition, but also for the scientific and interpretation analysis of the atmosphere of the result of Amelia. Next. And so the expertise and lesson learned in the framework of Chiaparelli ADM and the expertise in Mars observation and modeling have been put in perspective for the Amelia ExoMars 2022 and ADL science experiment. The ExoMars 22 would provide opportunity for a new direct in situ measurement, exploring altitude range not covered by remote sensing, but also with a special resolution that we don't have with other observation. And they will provide also ground truth for the surface and atmosphere, together with also the measurement done by the meteorological package on the surface of Mars that will provide important constraints for validation of Mars atmosphere models. I don't know if I have time. I just want to comment a little bit the inversion that, for example, the inversion that we observe that was showed by Bart in the last part of the descent. Actually, that was clearly it was an inversion which is realistic, and it was observed also by insight, but also at the same pressure altitude pressure level from Pathfinder and MER2. That is really something which should be investigated, and it's not possible to reproduce with the models that we have at present. So thank you.
All right. Thank you very much, Francesca. Since we're low on time, please, we're going to move on to the next speaker, but please have any questions in the chat and answer there. So Davide, I believe you're up. Please get ready. So
hello.
Davide,
hi. Yep.
Hello.
Can you hear me? Yes. Hi.
Yes. Davide Bonetti holds a MS in Aerospace Engineering from Politecnico di Milano, joined Deimos in 2005 and worked as a project engineer or manager in multiple projects in the Atmospheric Flight Competence Center of the Flight System Business Unit, including the ESA Roscosmos ExoMars program and the ESA program, among others. Since 2014, he is head of the Atmospheric Flight Competence Center, coordinating all Deimos mission engineering activities related with the ascent, entry, descent, and landing flight phases. Davide is currently involved in the ESA Space Rider program, leading the mission engineering activities for the re-entry module, and he's the project coordinator of ESTO, funded by the European Union. So Davide, please take it away, and please stick to the 10-minute time limit.
That's right. Thank you, Gregory, for the introduction. It's a pleasure being here all together, even virtually. Thanks for the invitation and the IPP committee organizing this. Yeah. Today, I'm going to present you the ESA-funded study MSPC, which stands for Mars Surface Platform Capabilities, and aims at exploring design options for an improved European Mars CDL system based on the lesson learned from Schiaparelli. The prime contractor is Thales Alenia Space, and I'm glad to present you a synthesis of the study in which Deimos Space contributed with its unique expertise in mission engineering for EDL systems for Mars exploration. Next, please. The key objective is to capitalize on the design heritage and post-flight analysis of the ExoMars Schiaparelli mission with the goal of improving European access to the red planet. The aim is to revise the EDL technological constraints and update the design of the EDL to improve the performance of a future European Mars mission to be flown between the 2030 and 2040. Next, please. To do so, we started from the lesson learned from Schiaparelli, which reached Mars on 2016, and worked together with ESA on a list of updated design assumptions and constraints. Those basically set the basis for the EDL design loop, performed at mission level by Deimos and at system level by Thales. And the results obtained helped the team in three key aspects. So first of all, get numerical evidence of the improved EDL performance achievable versus Schiaparelli. Second, quantify the increased mass and volume available for science. And third, drive considerations for technology roadmap aspects through a list of future developments needed in Europe. Next, please. Yeah, this slide gives an overview of the ExoMars 16 for those of you that are not familiar with the ESA Roscosmos mission, or if you didn't follow Bart or Francesca's presentation before. Briefly, in October 2016, the Schiaparelli EDL demo demonstrator separated from the TGO spacecraft and started our 3 days coasting before entering into the Mars atmosphere. It performed a successful ballistic entry and deployed the supersonic disc band parachute at the desired conditions. Strong angular acceleration were experienced by the IMU at the parachute inflation, and this basically resulted in an off-nominal sequence of events. And in particular, the 9 thrusters for the power landing were activated and shut down too soon at a too high altitude, resulting into a hard impact on the ground. And despite the unfortunate loss of the scientific instrumented platform, the EDL mission was highly accurate in the targeting of the landing site. And above all, unique telemetry was collected from the flight. So thanks to that, multiple post-flight analyses were performed in Europe since 2016, to understand the flight of this demonstrator, and lots of lessons learned were derived. This project, MSPC, exploits most of them and set the basis for future European exploration missions of Mars. Next slide, please. Yeah, a list of key system design facts and ideal mission assumption is shown here. The first thing to highlight is the fact that MSPC will be a scientific mission, improving, say, the scope of being a demonstrator that was set for Schiaparelli. There will be room for redundancy to improve, in particular, the avionics and the communications. And most of all, there will be more mass and volume for the scientific package. Key updates in the design include the parachute, the aeroshell structures, and other subsystems. At ideal mission level, it can be said that the ideal sequence is kept per Schiaparelli with some important differences. First of all, the probe separates closer to Mars, not 3 days before the arrival. The entry mass is increased by about 100 kilograms, keeping the probe diameter of 2.4 meters. The TPS design margins have been updated, and the parachute deployment is no longer mortar-based, but it's extracted by the pilot chute deployed at the lower Mach number. Next slide, please. So under these assumptions, we at Deimos performed multiple parametric simulations of the ideal missions, and the results are synthesized in this chart, which basically shows the constraint affecting the entry corridor on a ballistic coefficient versus flat angle plane. The gray region shows the feasible range of missions where all the constraints are respected. We can see that under the Schiaparelli design assumptions, 2 steep entries basically violate the TPS seat flux design limit, and 2 shallow entries violate the landing accuracy. The yellow dot here indicates the Schiaparelli design point for a ballistic coefficient around 75 kilos per square meter and a flat angle at entry interface point of about minus 12.4 degrees. The chart shows that as the entry mass increases, the corridor shrinks up to the point where margins are too small or equal to 0. For a BC of about 88 kilograms per square meter, equivalent to about 608 kilograms, the entry corridor is just 0.1 degrees. Next, please. Under the MSPC updated design assumptions, the entry corridor gets significantly wider. Now, 2 steep entries violate the load factor or the verticalization constraint that is imposed by the radar during the descent phase under the parachute. 2 shallow entries still violate the landing accuracy, but the constraint is now relaxed, and thanks to the increased accuracy of the separation closer to the EIT. For the MSPC BC target, the entry corridor is now 1.4 degrees, so it's much better than under the previous assumptions. And we can say that a reef parachute could further shift the blue constraint here towards steeper flat angle, further enhancing the corridor. And this could be needed for some specific landing sites on Mars. While this chart is valid for Schiaparelli landing site in Meridiani Planum, a wider planetary analysis has also been performed. In the next slide, please. This chart shows you the entry corridor width as a function of the landing site coordinates for a wide range of combinations. It shows that there is a clear correlation with the Martian topography and gives also a first indication of which area could be reached by the MSPC scientific mission. From these results, we can say that about 70% of the areas below MOLA 0 are accessible with an increased payload mass and an entry corridor compared to the Schiaparelli design. Next slide, please. Here, moving at system level, reconfiguration of the Schiaparelli was done to allocate resources for 3 types of landed platform while maintaining the aeroshell shape and size of Schiaparelli. The key drivers were the avionics redundancy, the maximization of volume and mass for the payload, and also the implementation of solar panel arrays. Design commonalities with the upcoming ExoMars RSP mission in 2022 were also taken into consideration by the Thales Alenia Space team. Next slide, please. Yeah, out of multiple reconfiguration options that have been explored, two are shown in this slide. On the top, we see the redesign of the main separation assembly and the significant reduction of TPS mass that is possible thanks to the updated assumption in the ideal mission analysis. And on the bottom, we see the MSPC pilot chute extracted parachute that is replacing the Schiaparelli mortar ejected solution, and that is a solution that is also adopted in the ExoMars 2022 mission. Next slide, please. Beyond the EBL system, the important updates have been introduced also at the lander system design. And in this chart, we can see the densely packed Schiaparelli lander platform on the left and the updated MSPC design on the right. The main updates introduced are the relocation of the RCS tanks and piping, which helps in the maximization of the central bay for the scientific payload, the redundancy in the IMUs, and the optimization on the antenna design for telemetry. And also visible here are the solar panels that are needed for the different MSPC mission durations that have been considered. Overall, about 100 kilos of extra equipment can be installed on MSPC in the same Schiaparelli arrow shape. Next, please. Yeah, multiple payload actually can fit into the volume available, enhancing the mission scientific return. Options of rovers, drones have been explored at mission level, resulting into small or limited capabilities. On the right side, the ExoMars RSP solution is also shown. And at the moment, we can say that MSPC stands in between the Schiaparelli and the next ExoMars mission. It's clear that for more ambitious exploration mission, the size of the mobility element grows, and of course, the size of the aeroshell must also be scaled up. The challenge for Europe is probably to set the right target for the next mission to Mars. Next, please. So in conclusion, we can say that the MSPC design improves the Schiaparelli demonstrator, increasing the payload mass by about 100 kilos and the volume available for science. It builds on the lesson learned from the unique telemetry of Schiaparelli and introduces several important design modifications at EDL and system level. Further design iteration, of course, are needed for a consolidation of the assumptions and the design options, and in particular for what concerns the TPS and the parachute subsystems. Next, please. And based on the current results, a list of suggested next steps for European technology has been derived by the team. And beyond TPS and parachutes, more advanced GNC solutions have been identified as a critical element to break the limit of ballistic entries. Game-changing concepts like supersonic retro propulsion and inflatable heat shields were also suggested. And to conclude, we hope that this input will be injected into the technology roadmap that ESA is elaborating for a future European exploration of Mars beyond ExoMars. Next, and thank you.
All right. Thank you, Davide, so much for that. We don't have time for questions, so please put them in the chat, and Davide, please answer if they come up. So we'll move on to the next group here with Jessica and Albert, who are both junior undergraduate students studying mechanical engineering and physics respectively. They are the team leads of a student design team that designs a Mars ascent vehicle, which participated in a 2021 NASA competition and was selected as a finalist. So Jessica and Albert, I believe you guys are up. Are you guys ready?
Yeah, thank you.
Okay, and please stick to the 10-minute time limit. There you go. Thank you, Tim.
All right. Thank you for coming to our presentation. My name is Jessica, here with my co-presenter, Albert. We present a low-mass Mars ascent vehicle concept on behalf of our team. a student team of 20 undergraduates and graduates at the University of Southern California. Next slide, please. So the challenges of entry, descent, and landing on Mars are such that large payloads present extraordinary technology and launch challenges for human Mars missions. In previous architectures, one of the largest elements of a human Mars mission has been the Mars Ascent Vehicle, or MAV, with wet masses exceeding 40 tons for a crew of 4. So we propose a lower mass design to deliver a crew of 2 from the Martian surface to the low Mars orbit. It is a single-stage bi-propellant vehicle with dry mass less than 5 tons and wet mass around 17 tons. This concept was initially designed and submitted to participate in the NASA RASCAL competition. Next slide, please. The concept of operations is as follows. After a surface day, the crew will ingress into the MAV through an extendable pressurized tunnel between the surface rover and the MAV. The crew will change into IVA suits inside the rover, then exit into the tunnel and climb up a ladder to the MAV. After ingress, the MAV will hold on to the pad until a launch window approaches, and when ready to ascend, the MAV will lift off and reach an altitude of 150 kilometers, where it will then initiate a burn maneuver, perform a rendezvous to approach the Earth return vehicle, and perform docking. After crew transfer, the MAV will be decommissioned. Next slide, please.
Once the MAV has successfully completed its ascent phase, it can begin its autonomous process of performing a sequence of maneuvers. The sequence path can be seen here. The entire sequence can be divided into 5.5 hours, spinning a total of 3.8 kilometers per second of delta V. The sequence is based on Soyuz fast-track orbital sequence and is made possible by SSRU, reliable engines, and thin Martian atmosphere. Next slide. The MAV comprises of 6 functional systems. The table on the left shows the estimated mass of each system function. For each subsystem, we use a 20% margin to account for winging, tubing, and etc. The table on the right shows the primary materials for some of the main structural components. The materials were selected based on their structural and thermal properties, as well as selected to minimize the mass while maintaining manufacturability and a high technological readiness level. Next slide. The dome of the MAV is constructed from a carbon fiber composite with a thickness of 8 millimeters. The radome protects some of the communication antennas and is made of fiberglass cured with cyanide ester resin to allow for signals to pass. The dome and radome are connected with structural adhesive and fasteners to transition between 2 materials. The bullet-like shape of the dome helps to minimize drag that will be exerted on the MAV during the ascent. Next slide. The fuel tanks are in a nested toroidal formation with a diameter of 3.75 meters and a height of 1.49 meters. The design was chosen over a traditional cylindrical fuel tank configuration as a way to reduce the overall height, and the outer fuel tank has a volume of 7.21 cubic meters, and the inner oxidizer tank has a volume of 7.24. And next we have the propulsion system. Next slide. The current propulsion design utilizes MMH and MON25 combination with a ratio of 1.6, a turbopump feed system. And the MAV will be a single stage to orbit. And MMH and MON25 was chosen over other popular fuels such as liquid methane, liquid oxygen, and liquid hydrogen and liquid oxygen based on its ability to simplify the propulsion system. MMH in Mon 25 is not cryogenic, so the storage and thermal aspects are less complex and require less energy. In addition, MMH Mon 25 can be restarted easily, so it does not need to consume finite ignitable sources since it's hyperbolic. Next slide. So this is a schematic of the entire propulsion system, including fuel oxidizer tank, heat and pressure tanks, valve, and tubing system.
Next slide, please. Yeah, so the MAV's avionics system is responsible for automating the mission flight time, controlling the thrust vectoring system, monitoring vehicle status and operational readiness, perform monitoring, data processing, communications, tracking, guidance, navigation, and control, and also the electrical power distribution. Next slide, please. A trade study between different power sources revealed that using only batteries would provide the highest energy density option based on our short mission duration. As for batteries, the lithium MnO2 batteries were chosen due to their lower resistance coefficients, lower risk of thermal runaway, and superior shelf life. Next slide, please. So the environmental control and life support system takes care of the suit selection, oxygen generation, consumables, waste management, temperature and humidity control. And we'll only talk about the suit selection and waste management here because of the time limit. So the Advanced Crew Escape Space, or ACES suit, was chosen. It is pressurized in case of loss of cabin pressure or pulling in the lower body. It also provides protection from extreme heat and cold, fires, and contaminated atmospheres. And after comparing hygiene, comfort, duration, cost, usability, development, and mass for various options, the team decided on the use of the maximum absorbency garment with Apollo bags for the waste management due to their low mass and budget requirements. Next slide, please. So for a thermal control system, the MAV thermal control system maintains optimal temperatures for subsystems. The major elements of the thermal subsystems are a chem-glaze V306 black paint coating for greater heat retention, 20 layers of aluminized Kapton multi-layer insulation, which is applied to the propellant tanks for crew cabin, including the avionics bay, and also a 5 square meter radiator structural panel for excess heat rejection, patch heaters on the propellant tanks, and an additively manufactured mechanically pumped fluid loop with CFC11 as working fluid to provide efficient and robust active control of heat transfer within the MAV. Next slide, please.
So the development plan of MAV is divided into multiple phases according to NASA project lifecycle, with the estimated 50 percentile uncertainty cost of $14.47 billion. This is our total development plan, and our cost estimate was calculated through NASA's PCEC software. Additionally, the open source Excel adding Argo, which is a Monte Carlo simulation tool, was used to determine the uncertainty analysis to generate a uncertainty adjusted parameterized estimate graph. So based on the data provided on the slides, we are confident that the cost would not exceed the previous plan.
Okay, I think that was it from Jessica and Albert. Thanks for that, presenting that architecture of a human Mars descent vehicle and showing us, touching on all those different systems. Okay, we're going to keep pressing on here. Again, feel free to leave questions on the chat, but I'm going to hand it over to Michelle to introduce the last two talks of our session.
Okay, thanks, Gregory. So I'll keep this short. Our next presenter is Dr. Ashley Corzin. She's an aerospace engineer at NASA Langley Research Center, and her specialization is on propulsive descent for landing on the Moon and Mars currently. Take it away, Ashley.
Currently. Thanks, Michelle, for leaving the door open there. So let's actually go to the next chart. So what I want to talk about is plume surface interaction, specifically for Mars, that we're in the Mars exploration session, or you'll hear me call it PSI for short. They say a picture is worth 1,000 words. This is a photo I think a lot of folks are very familiar with at this point. This is the Perseverance rover being lowered underneath the sky crane during the terminal landing phase of the Mars 2020 mission at Jezero Crater on Mars just from this past February. And what you see in this image, or rather what you don't see, is the Perseverance rover. You have a near total visual obscuration due to the dust caused by this propulsive landing event on Mars. So this is a really great illustration of real life plume surface interaction occurring, during what was ultimately a highly successful landed mission. Next chart. So if we look at a more formal definition of plume surface interaction, it's a multi-phase physics problem. It's highly complex between gas phase physics, granular phase physics, vehicle impacts, temporal considerations. There's a lot going on. So we're going to break it down a little bit on this chart in particular. We're specifically talking about, with PSI, the environments on your lander or even your surface assets and infrastructure that are arising due to the impingement of hot rocket exhaust on the regolith of planetary bodies. These can be bodies with atmospheres or bodies like the Moon that lack atmospheres. So the first thing you notice in this image is that gray bar up at the top is representing your lander, and those little cones at the bottom are your nozzles from your descent system. Coming out there in purple, this is the gas phase of the problem. This is the starting point, you could say, for PSI. So all of your gas phase plume physics here, you have the flow expanding out of the nozzle. It hits the ground. Some of that flow is going to turn right back around and come up toward your lander, but a lot of that gas is also going to start diffusing into the soil or the regolith below your vehicle. This gets you to part two for PSI, or cratering or erosion. You don't necessarily have to dig holes underneath the vehicle, but you're going to start fluidizing and creating motion, of the granular phase of this problem. And then thirdly, you have the ejective phase. So all of the material underneath the lander that is being liberated, it has to go somewhere. It can go straight back up. It can be ejected at various angles and velocities out to the side. And that's really the third phase of PSI. And to get your PSI environments correct, you need to get all three of these parts of the problem right. Can we click once, please? So lander effects, I think it's pretty apparent when we start talking plume physics. You have reverse flow, you have very complicated flow, highly unsteady flow going right up into the base of your lander. Can potentially cause structural damage, but additional considerations would be maintaining controllability and stability of your vehicle as you get close to the surface. Click one more time. Example of cratering. I think everyone's very familiar with Apollo. You have scouring of the surface in some of the Apollo imagery, but you also are going to dig, in some circumstances in certain landing sites, sizable holes underneath the vehicle. And click one last time. This is an example of the camera cover from the InSight Mars lander. So this cover eventually did come off, but this is the result of impacts of these particles onto your critical parts and potentially instruments that are important for science on your lander. Next chart. So what we want to do now is take a little bit of a walk through history in the context of exploration at Mars. So of course, this starts with the Viking missions in the 1970s. Much like a lot of our other Mars EDL technologies, there was a ton of work done on trying to get a handle on understanding of fundamental physics and then vehicle mitigation for plume surface interaction. Viking was heavily concerned with PSI, and the testing that they conducted during that era is still heavily relied upon today. I think a lot of folks have seen that image in particular in the lower left on the screen showing the 18-bell showerhead nozzle that was eventually selected and then flown on both of the Viking landers. And this was done to mitigate PSI by keeping your direct impingement pressures below about 2 kilopascals on the surface, but really to diffuse that engine exhaust from causing major problems underneath your system. Next chart. Jumping forward a little bit to Mars Science Laboratory, you have the sky crane was used for the first time, and a big reason of going with the sky crane was with the intention to mitigate PSI effects and damage to the science payload. Even at 63 meters above the surface, we're starting to see from MARTI camera imagery some slight alteration underneath the vehicle due to the Mars lander engines. There's 4 distinct kind of sets of craters on the surface that are shown there in the bottom center. So the sky crane was ultimately successful in doing this, but even at a relatively sizable height above the surface, you have some pretty significant surface erosion still occurring for this mission. Next chart. We did skip Phoenix, but I did want to talk about InSight in particular because we did do a stereo reconstruction. So InSight landed in 2018. This is a little bit different landing system, so a direct kind of pallet-style lander with a pulsed engine system underneath. But InSight, and you can see pictures online as well, where the legs of the lander are very, very much buried in what looks like very sandy regolith. But InSight, as far as Mars landers go, is a smaller landing system, and you're still digging pretty sizable craters underneath the lander just from its terminal propulsive landing phase. In fact, you had one footpad, in the case of InSight, right on the edge of a crater rim. And InSight, due to its science objectives, had a pretty stringent tilt requirement. If that crater had even been just a little bit larger, there of course remains the possibility that we could have violated that tilt requirement. Next chart. So lastly, this brings us to Mars 2020. Again, you use the sky crane in this to do landing in this case, just like MSL did. We can't get enough of these images and the video from the EDL cameras, but this is the first time we have data from both uplook and downlook cameras on both the descent stage and the rover, giving us visualization of PSI over a really broad set of temporal scales. So if we look just to the progression of images that are in the upper right, as the rover is being lowered toward the surface, you begin to start seeing dust being kicked up off of the surface. There's no evidence that we've seen from Mars 2020 that you dug any craters per se, but just as a fact of approaching the surface and then spending a certain amount of time hovering about 8.5 meters off the surface, you're really starting to kick up a lot of dust, almost getting you to a complete visual obscuration of the rover by touchdown. And then you begin to see, additional longer-term temporal effects as the dust begins to dissipate as the bridle is cut and the sky crane begins to fly away. The only other thing we want to point out here is, a little bit of debris on the Perseverance rover deck, but that image with the big orange circle on it in kind of the lower left quadrant of this chart is showing some paint erosion from an instrument on the surface of the lander. This erosion, is the result of the rover descending through having a lot of dust and particles and potentially larger pieces of surface elements, moving at high velocity and striking these surfaces. So this is phenomenal to actually see PSI in action in this case. Next chart. So what is NASA doing about some surface interaction? We have a multi-year Space Technology Mission Directorate investment in closing our knowledge gap related to PSI. 3 critical elements to this project. We have a very significant computational modeling and simulation element where we're developing and validating a multi-phase flow capability to be able to get your gas phase physics, your erosion physics, and those ejecta physics correct, and to be able to do them at multiple scales such that you can eventually apply this to provide quantitative information on PSI environments to flight systems. Secondly, we have ground testing. There are 2 significant ground tests, both occurring in vacuum chambers as part of this project, and I'll touch on those a little more detail on the following slide. And the third element is flight-focused instrumentation. Specifically, we're maturing a millimeter wave Doppler radar to help us, observe and quantify ejecta physics in flight. And then we also are very closely linked with SCALPS, which is a stereo camera system, the first iteration of which will fly on the Innovative Machines lunar lander early next year. Next chart. So I mentioned a little bit about those two ground tests, in part to validate our computational tools and just understand PSI physics better in general. We have a need for relevant test data and testing in relevant environments. Those two ground tests that I've mentioned are our first opportunities, almost in spiking, to obtain what can be considered flight-relevant PSI data, while also emphasizing highly controlled, very well-characterized ground testing such that these data are useful for the validation and just general maturation of high-fidelity physics modeling capabilities. That first subscale vacuum test, you're looking at a total thrust of about 2 pounds force. And just for scale, in the lower right image of this screen, that's a 6-foot-tall person. That's the size of our test article in this case. It's a very small-scale test. On the complete opposite end of that spectrum is our large-scale vacuum test with thrust levels, in excess of 5,000 pounds force. That's a hot fire engine test. So you have high enthalpy flow impinging upon mechanical lunar regolith simulant in an extremely large vacuum chamber. So just for scale, I have an image. This is the In-Space Propulsion Facility, which is part of the Armstrong Test Facility, or formerly Plumbrook Station, in Ohio in the U.S. And barely visible, the little orange dots on the screen are actually safety equipment. So those are people, just giving you a sense of scale for the differences between these two tests themselves. So all of this is focused on giving us the ability to move from qualitative inputs to people designing landers and exploration campaigns, moving us much closer to quantitative, substantiated with data environments and mitigating impacts to PSI. So next chart. So just in closing, make the note, we're very focused on Mars, and we've shown some examples here, but all propulsive landers are affected in some way by PSI. And I would add to that, if you're going to do any sort of propulsive ascent off of the surface as well, you are going to have to make considerations with PSI. We are the landing phase. We are the L. We're kind of the forgotten letter in EDL when it comes to dealing with these types of effects. But when your landing paradigms change, PSI returns to the risk list. And what I'm getting at here is as your vehicles become larger, PSI doesn't go away. If anything, it becomes something that is going to be an increasing challenge that you're going to have to deal with, particularly if you start talking the size of the systems for something like Mars sample return and eventual human exploration of both the Moon and Mars. A lot of times we're very focused on near-field vehicle effects, but when you start talking to the end of sustainable exploration, something where you need to be landing somewhat in proximity to existing surface assets or utilizing other surface infrastructure, PSI becomes increasingly important as something you maybe need to mitigate against. So just lastly, looking ahead, there's a couple more posters at IPPW, as well as a presentation on the EDL cameras in the EDL tech session coming up on the 20th. And we will have multiple sessions at the 2022 AIAA SciTech Forum focused just on PSI and dust itself. So we hope you'll be able to join us then. Last chart. Yeah. And I'll take any questions. Probably have to do them in the chat.
Yeah, thanks, Ashley. We do need to move on. I see a good question for you from Sam Albert, if you have a chance to answer that. So our final speaker for the session is Andrew Ball. Andrew is a systems engineer at ESA S-Tech, where he's been since 2008. He worked previously on Rosetta, Huygens, and ExoMars 2016 and 2022, and Andrew has participated with us in all but 2 IPPW since 2003. So great to see you again, Andrew, and we look forward to your talk.
Okay, thanks, Michelle, and hello, everyone. So I'm just going to give you a quick overview of one of several mission concepts that we're currently looking at in the context of what Sanjay was explaining earlier with regard to planning of future exploration activities within Europe. Next slide, please. So this was work performed starting last year in that context to look at putting a small orbiter around Mars with a payload capability supporting exploration and science. using aero capture. So, in other words, Mars orbit insertion using the atmospheric drag instead of the classical chemical propulsion methods. And this would offer potentially mission-enabling mass and/or mission duration savings for future larger missions, whether they're at Mars or elsewhere. And it seems clear over the rather long history of aero capture research that a demonstrator is needed, even if itself it's suboptimal versus chemical propulsion alternatives. So aero capture was recognized already many years ago when the Aurora program, out of which emerged the ExoMars missions, was formulated. So we started with the idea of a dedicated launch on a small launcher, Vega C, with an upper stage derived from the LISA Pathfinder propulsion module. That would afford us about a 2.6 meter fairing diameter and 378 kilos onto an Earth-Mars trajectory. Next slide, please. So this is just a recap of the aero capture sequence. So you see with number 1 in the bottom left-hand corner there, you arrive from the interplanetary trajectory, separate from the carrier, enter the atmosphere, and then perform a maneuver in the atmosphere to decelerate to be captured into orbit, exit the atmosphere onto an initial transfer orbit, and then to avoid a second pass down into the atmosphere, you need a delta V to raise the periapsis, and then probably a cleanup delta V periapsis to correct for apoapsis error to achieve the final operational orbit. Next slide. I'll skip that. Next slide, please. So we started with the idea of keeping it very, very simple using the existing European Mars hardware heritage, and then the Schiaparelli. You see the front shield top right, the rigid shield there, 2.4 meters in that case. So we applied the starting point from one of the papers in the literature about aero capture for using a rigid separable drag modulation technique with a drag ring. There are alternative techniques that you can see in the slides here for inflatable or deployable decelerators. And in fact, during the course of the study, if you go to the next slide, this shows where we ended up with the concept of having a hybrid drag ring. The circular features in blue there indicate notional stacked toroids for an inflatable outer section of the drag ring, and then that whole conical section would separate during the atmospheric pass once enough deceleration has been achieved to achieve orbit insertion, and then what remains then exits the atmosphere, and the orbiter, the turquoise rectangle there in the diagram, would separate from the remaining part of the aero capture module, transition to a 3-axis stabilization and perform its orbital mission, and the remaining propulsive maneuvers. Next slide. So we started off with some assumptions about entry speed, about 5.5 kilometers per second, simple drag modulation triggering based on IMU data integrating the deceleration. We targeted a 5,000 kilometer apoapsis altitude for the insertion, in the knowledge that we should revisit this later based on an orbiter mission to make the final orbit something that could be used by an orbiter payload for science or technology purposes. And since this is a demonstrator mission, we would want to transmit essential telemetry during the aero capture maneuver and until the next periapsis, and then the full data set after insertion into the stable orbit. And we have to bear in mind that as with the Mars lander, you'd have to comply with planetary protection regulations. So the diameter for such a launch, as described earlier, which would be a dedicated launch, would be about a 1.7 meter diameter heat shield, Going smaller would mean too high a density of the resulting satellites, and going larger would be too heavy for the Vega C launch. We started with an assumption for a ballistic coefficient ratio for the before and after drag ring separation configurations of 7 as conservative. Perhaps we could go a bit higher. Next slide. This is just to show one of the nominal trajectories that you would experience during a pass. So mission time horizontally, and the blue curve on the left shows the altitude as you come down to below 40 kilometers or so. And then rather than proceeding to land on Mars, we come out of the atmosphere again. And you can see the heat flux and heat load as the red and the green curves there on the left, both of which are quite moderate with regard to designs for Mars landers. And on the right, you can see deceleration or drag force as the red and green curves there, and the sudden drop, the discontinuity that you get on the drag modulation event when the drag ring is separated. Next slide. So it's important to be able to target the aero capture module sufficiently precisely, and we based our assumptions on those of ExoMars 22, scaled for the slightly shallower flight path angle that would be required, and this would still keep us using the delta door, classic delta door techniques for tracking, would keep us within a flight path angle corridor of about 0.75 degrees. And as I said, the thermal loads are quite moderate. Next slide, please. And it's important to make sure you have enough control authority for the drag modulation maneuver, and this becomes difficult for higher and higher masses, and the simulations yielded an upper limit to this technique for the assumptions we made of 1.3 tons, so well above what we would consider. So we were in a good place in that respect. And we also have some margin in terms of the ballistic coefficient ratio. We could go down a bit lower if necessary. As you can see in the plot on the right shows the relative flight path angle. So the vertical extent of that pink area represents the width of the corridor, and you still have about 0.75 degrees corridor width, even at a ballistic coefficient ratio of 4, which is probably below where we would want to be. So using the dedicated launch assumptions and an assumption for the carrier module mass of 150 kilos, we would be looking at something like an entry mass of 228 kilos, and one could actually go smaller than that to make it more of a piggyback launch, which could open up other launch opportunities, piggybacking either on another or another mission internationally. Next slide, please. So in conclusions, we established that with currently existing European technology from the previous European Mars missions, a small aero capture mission is possible. And for a dedicated launch, it would be at about 228 kilos for the Vega C assumption, and the masses of the drag ring stated there. What we realized along the way was the center of mass management is particularly important, and we would try to minimize or eliminate the need for ballast mass, and so that feeds back into studies going forward on the shape of the aeroshell. And of course, we assume a technology payload to monitor the actual aero capture maneuver. Next slide, please. And there are trade-offs to be done between a dedicated versus a lower mass piggyback version, as I mentioned. We would like to eliminate the need for a separate carrier module and have that functionality merged with the kick stage or orbiter module in the case of the small mission. And we need to do the stability analysis before and especially after the drag modulation event, and do a trade-off between the heritage 70 degree sphere cone front shield versus putting the conical section further back. And we'd like to look at linear versus spin separation of the drag ring. And other constraints arising from the hypersonic environment, of course, to make sure that you have clean separation of the drag ring without contact, and to assess options for the GNC algorithms, to look at including the inflatable outer section to the drag ring, which provides something that's additionally attractive in terms of tech demo, and to perform a more detailed analysis of what the orbiter could do. So, and finally, we would want to compare this with a chemical propulsion Mars orbit insertion of something of the same size. So we'll be engaging with industry and the Mars community over the next year or so with some further studies performed with ESA and with the European industry community. Thank you.
Thank you, Andrew. We've got some questions in the chat for you, so if you could attempt to answer those before you go. I'm going to hand it over to Gregory to wrap up the session. I want to thank all of the speakers.
Yes, thank you everyone for participating today. Thank you to my co-chairs, Michelle and Oskar, and all of the great talks that we had today. Also want to thank the POC and the IOC. I mean, this is great that we can still organize IPPW virtually, and I'm really hoping we can see everyone next year in person, because I miss everyone. As mentioned earlier, the materials will be posted on the website, so look out for that. And in terms of next sessions, there is a student social right after this, and I encourage a lot of the students to go to that. Again, there's been a lot of great students who have participated in IPPW and are now professionals amongst us and doing a really, really great job. So please join that. And I think the next time we will reconvene is on July 20th for the EDL Technology, Science, and Instrumentation session. So feel free to register for that, and we will see everyone on July 20th. Thank you, everyone. Have a great day or night.